Hello and welcome. My name is John Horvath, and my presentation today is about using the cone penetration test for site characterization. And I'm going to illustrate this using a case history that involves the Hudson Valley Varved Clays. These are very significant Pleistocene Epoch soil that is found throughout the northeastern United States in the states of New York and New Jersey, very extensively throughout the New York City area. And they have not received a lot of treatment with respect to using the cone penetration test in this type of material. I've broken my presentation into several segments. You see the outline here. I've done this, this is a fairly lengthy presentation, so this will facilitate presenting the material in a logical fashion and will also facilitate your viewing. You may find it convenient to watch this presentation in segment by segment as you have time. Well, let's start out with a little bit of background discussion as to why I decided to make this presentation. Back in 2020, I created a YouTube channel, and I posted the first of what became a series of narrated PowerPoint presentations on various topics that related to my research and professional practice. That first presentation that I posted last year discussed the 77 years of geotechnical and foundation engineering history at the John F. Kennedy International Airport in New York City. Construction on this airport began in 1943 in the midst of World War II. One of the reasons I chose Kennedy Airport was I have done a lot of work there beginning early in my professional career in the early 1970s and at various times since then. And I have also used Kennedy Airport as a significant case history study for the work I've done related to tapered piles. And I have a presentation on YouTube that deals with tapered piles, and I've written a monograph that deals with tapered piles. But my focus here today is not tapered piles, it's site characterization. And one of the themes of my presentation about Kennedy Airport was how much site characterization technology had changed during that 77-year time span between 1943 and 2020. And one of the very significant aspects of that change was the commercial availability and technological evolution of the cone penetration test. The CPT was first used at Kennedy Airport in the 1980s, and to the best of my knowledge, that was one of the earliest large-scale uses of the cone penetration test in the New York City metropolitan area. The New York City metropolitan area has been relatively slow to pick up on using the cone penetration test compared to certainly other parts of the world and even other parts of the United States. The cone penetration test remains a staple of site characterization at Kennedy Airport to the present, and I would see no reason why it would not continue to be so into the foreseeable future. The subsurface conditions at Kennedy Airport are very, very conducive to using the cone penetration test. Well, this presentation discusses another site in the New York City metropolitan area in which the cone penetration test was recently used as an in situ investigative tool. There are several goals I have for this presentation. The primary one is to discuss a very common subsurface artifact or result of the Pleistocene epoch known as glacial-lacustrine varved clays. This type of soil is found very extensively throughout the New York City metropolitan area and is very different from the Pleistocene subsurface conditions at Kennedy Airport, which are all coarse-grained soil, glacial outwash. Even though the subsurface conditions at both Kennedy Airport as well as the case history site I will discuss in this presentation were affected by the exact same sequence of Pleistocene glaciation. Now, as you probably know, varved clays are found in many other places throughout the world, the United States, that were affected by Pleistocene glaciation. So I would think the contents of this presentation have a global appeal that is well beyond just the Hudson Valley. Another goal I have for this presentation is to illustrate that the cone penetration test is not just a big project site characterization tool as it has been at Kennedy Airport. Most of the projects at Kennedy Airport, certainly in recent years, have been for new passenger terminals, things like that, fairly large-scale projects where there were dozens of borings, dozens of cone penetration tests that were performed. I found that the cone penetration test can be a very cost-effective tool for projects of all sizes. And one of the several reasons I chose the case history I'm going to talk about today is that it was a relatively small project. It involved a very modest-sized commercial building, 6 conventional borings, and two cone penetration tests were performed. So the project I'm going to talk about today is very typical of the very modest project that I think any geotechnical or foundation engineer might encounter in their everyday work. And I emphasize this because in geotechnical and foundation engineering, very often we have various tools or technologies, and somehow they get a reputation that they're great, but they're only cost effective on big projects. And that simply is not the case with the cone penetration test. If you can mobilize an ordinary drill rig, you can mobilize a cone penetrometer rig as well. Another significant goal of both this presentation as well as the earlier one dealing with Kennedy Airport is to foster greater geotechnical and foundation engineering awareness and use of the cone penetration test for site characterization. And this is especially true in countries such as the United States, where there still is what I think is an over-reliance on the standard penetration test, which quite honestly is probably the most non-standard in situ testing methodology that there is. A very significant corollary goal of this presentation is to illustrate the benefits of the cone penetration test to other geoprofessionals, such as professional geologists who study sediment processes and outcomes, such as those associated with the Pleistocene Epoch. In my experience, many other geoprofessionals, such as geologists, are not aware of all the information that can be extracted from the cone penetration test. Some of the site characterization issues that I think are of interest to both geotechnical and foundation engineers, as well as geologists, are things such as stress history, as well as what we now refer to as the behavioral age versus the geological age of a soil stratum. And as we'll see, they are not the same. A given soil stratum only ever has one geological age. It's when nature placed it, or if it was the result of human activity. On the other hand, behavioral age is something that can be reset by any number of natural and human mechanisms. The motivation for this presentation, as well as the earlier one about Kennedy Airport, derives from my firsthand appreciation of the wealth of soil properties and parameters that can be inferred from a cone penetration test sounding, granted, in soils that are amenable to using this tool. As we know, there is no such thing as an all-purpose exploration tool. We have many different in situ testing tools in geotechnical and foundation engineering, the standard penetration test, the dilatometer, the cone penetration test, the pressure meter. each of these tools has conditions that it is optimal or amenable for use in. One of the reasons that I've become such a fan, if you will, of the cone penetration test is that I've used it extensively in my practice-oriented foundation engineering research that goes back now to the late 1980s, as well as in design practice in recent decades. So I have had a lot of firsthand experience with using the cone penetration test in both research and practice for well over 30 years now. Now, just to wind up this background discussion and before we get into the heart of the presentation, I want to be completely transparent in a professional and ethical manner and emphasize that I have received no financial compensation from any organization or individual to either promote the cone penetration test, to make this presentation, or any other presentation I have on my YouTube channel. And I emphasize this because we've all seen in recent years that, things come out that some big name academic professor, he or she decades ago may have written some paper promoting some type of food or something like that. Well, it comes out decades later that they were paid by the food industry or whatever to do that sort of thing. So people are often wary about, if they see somebody promoting something, they figure there has to be some agenda. I have no agenda in that regard other than I just have become a fan of the cone penetration test. However, since the 1980s, there certainly have been organizations and individuals who have provided me with raw data from many locations, not just the United States, but from around the world. And this was always done on a pro bono basis for research purposes. I was engaged full-time in academia until 2014. So a lot of it was really for my academic research. And there were no expectations of what I would do with these data, except in most cases, whomever provided me with the information asked me to please keep the source of the data as well as the exact location of the sites where the data was obtained confidential, and this was simply for client confidentiality, which I certainly respect. Now, I will, throughout this presentation, I may mention the name of an organization or product, and this is really just for informational purposes. I'm not promoting or endorsing that organization or product. So as I said, this presentation, as well as the early one about Kennedy Airport that I will be referring to points throughout this presentation, do not have an underlying hidden agenda in terms of being a paid promotion for the cone penetration test or any other technology. As I said, this is really a term that I've heard people use in the past, for the good of the order, as they say. It's just my contribution to the profession of civil engineering as well as geology for the advancement of the state of knowledge with respect to site characterization for geotechnical and foundation engineering purposes, and as I said, also for the benefit of professional geologists. Let me next discuss a very brief review of cone penetrometer fundamentals and resources. This is not going to be a presentation where I go through the details of the cone penetration test. I want to emphasize that the true cone penetration test, that is the focus of this presentation as well as the earlier one on Kennedy Airport, uses a cone that has a conical tip with a 60-degree apex angle, a 10 squared centimeter projected tip area, although a lot of modern cones are often 15 square centimeters. In fact, as we'll see, the 15 square centimeter cone was used for the case history I'll discuss today. And the cone is pushed at a constant rate of penetration. And this type of cone had its origins in the 1930s in the Netherlands. So for many years in the 20th century was referred to colloquially, at least in the United States, as the Dutch cone. When I first learned of the cone penetrometer as a student and an entry-level engineer, late 1960s, early 1970s, I heard it in the United States universally referred to as the Dutch cone. Now, I emphasize these details because I've seen in recent years that the term cone penetration test is nowadays used very loosely and often incorrectly for a wide variety of other penetrometers. Penetrometers nowadays come in many different diameters. There are things that are called mini cones, for example, and there are also cones that have a much larger tip area than 10 or 15 square centimeters, as well as installation methodologies. There are cones that are driven by impact into the ground using technology similar to what is used to perform the standard penetration test. So you have to be very careful. And there are also devices, for example, I've seen small handheld devices that are used for testing pavement subgrades. So for example, in the road pavement or airfield pavement industry, there's a cone that has just been developed for testing pavement subgrades. So I emphasize this because, as you'll see, the vast majority of the interpretation that we do of the cone penetration test for site characterization is based on empiricisms, empirical equations. And these empirical equations were developed for a very specific device that meets these criteria that I've enumerated here. So they are not necessarily correct for other types of cones. So you want to be careful about that. Now, the original cones that were developed in the Netherlands during the 1930s measured only the vertical resistance force to cone penetration at the cone tip, and this was done mechanically using pressure gauges. And this resistance force was expressed as a stress and given the notation lowercase q sub c. But with the development and miniaturization of electronics in the latter decades of the 20th century and into the present century, certainly a lot of additional parameter measurement capabilities have been added to the cone penetration test. The two most widely used versions of the cone penetration test at present are the piezocone, and I will use this notation, CPT lowercase u. And this measures the tip resistance, Q sub C, the sleeve friction, F sub S, and the pore water pressure at what we now refer to as the U2 filter location. And the U2 filter location is just behind the tip as I'm showing you here. And I want to emphasize that because there was a U1 filter location on the face of the cone itself. If you look at older literature, you will see reference to pore water pressure measurements made at this U1 location. There are actually experimental or research type cones that measure the pore pressures at both locations. And this is important because in a lot of soils, the pore pressures at the U1 and U2 locations at the same depth in the same soil will not be the same. In fact, they can be very different. So where the pore pressure is measured is very important. Again, all of the correlations I will be using in my presentation today are based on this U2 location. So be wary if you look at some older literature, you may see this U1 location referenced. Both of the pore pressures at either location are referenced to U sub O. Now, some people call this U0, U0. This is, to me at least, is U sub O because it's the static or overburden water pressure. The other version of the cone that is widely used at present is the seismic piezocone. Some people call it the seismic cone. This is the notation that I'll be using for it. And it also measures the shear wave velocity. Now, the cone that was used for the case history I'll be talking about today was this cone, 15 square centimeter projected area. One of the cones also measured shear wave velocity and the pore pressure at the U2 location. Now, there are other variations of cones I'm not going to get into that measure other parameters. People even develop cones that have a little camera built into it. So you actually get a video image literally as you push the cone into the ground. So really there's been a lot of advances due to the miniaturization of electronics. But these are the two cones that really are the backbone that we use at present. Now, I'm going to assume that you have a basic knowledge of both the piezocone and the seismic piezocone. If you're new to this technology or don't feel that you know this technology very well, a really excellent English language primer is the NCHRP Synthesis 368. You can find copies of this at various sources online. This was produced here in the United States by the Transportation Research Board back in 2007. It was done under contract as these syntheses are done. And the research was sponsored by the American Association of State Highway and Transportation Officials, as well as the Federal Highway Administration, which is part of the United States Department of Transportation. Now, some of the material in this document, it is 14 years old now, especially that related to the interpretation of the measured data as soil properties, is a bit dated. I wouldn't say it's wrong per se. Simply in the 14 years since this was published, and I'll just say as an aside, having done NCHRP syntheses, there's a long lead time on this. This may have been published in 2007, but I wouldn't be surprised if the research was concluded in 2004, 2005. There's often a multi-year time lag between when the research report is submitted and by the time Transportation Research Board actually produces a hard copy document. And as I say, I say this from firsthand personal experience, having done 2 NCHRP syntheses related to geofoam. So all my point is that there are, for a number of the relationships you'll see in this document, there are some newer, more accurate correlations and methodologies that have been developed. But it's still, overall, it's a really excellent document. It's a good, excellent introduction to the cone penetration test and its many uses in geotechnical and foundation engineering practice. So I highly recommend this as a very good primer to the subject if you're not familiar with the cone penetration test. Now, I want to emphasize that all the interpreted soil properties and parameters that I present subsequently, as well as those that I presented in the last year in the presentation on Kennedy Airport, are all based on or derived from published empirical correlations that have been developed by others. Now, there have been certainly countless publications about the cone penetration test in general and its more recent evolutionary variants such as the piezocone, the seismic piezocone in particular. But I have personally found the most useful practice-oriented published work in recent decades has been produced by Dr. Paul Main, who just retired from Georgia Tech in the last year or so, and Dr. Peter Robertson, who retired from the University of Alberta several years ago. I know both of these persons personally, especially Dr. Main, and certainly have the highest regard for their research, which has been conducted over many decades with their graduate students and other collaborators. So just about all of the work that you'll see, all of the relationships that I used to prepare this presentation, as well as the earlier one on Kennedy Airport, based on work by these two people. And what really sets their work apart is that in addition to their own original research, which is substantial, both of them have curated and incorporated the published work of many others around the world into their work. And not only that, but they have always focused their work to be practice-oriented syntheses of the current state of cone penetrometer knowledge. So from many perspectives, the work produced by these two people are really excellent for site characterization purposes. Now, most of the correlations in the interpreted results that I'll shown in this presentation, as well as the earlier one at Kennedy Airport from the published work of Dr. Main. He's presented his work at various theme papers. Very often these were keynote lectures at professional conferences, as well as PowerPoint presentations presented at invited lectures, some of which I've attended personally. And to me, the best way to access these papers and PowerPoint presentations is to visit Dr. Main's. He still maintains a personal webpage at Georgia Tech, and you can find this easy enough via online search. I've also extensively used the work of Dr. Robertson, especially in the last few years. I've used Dr. Main's work for many, many decades now, going back to the 1980s. Dr. Robertson's work more recently, after meeting him in person a few years ago and attending actually an all-day workshop he gave at the University of New Haven in Connecticut, discussing the cone penetration test. I've especially used Dr. Robertson's work related to soil behavior type, as I'll talk about later, as well as soil structure, sometimes referred to microstructure. And this relates to the aging, cementation, and other environmental factors that can influence soil. And when I say environmental factors, I don't mean that in an environmental chemistry or biological sense. I just mean things such as the natural chemistry of groundwaters and things like that. In particular, Dr. Robertson is a leading proponent of the concept that the cone penetration test should be used primarily for defining what he calls soil behavior type, not soil particle size and plasticity per se, as has been done in earlier decades of cone penetrometer development. All right, as we know in traditional geotechnical engineering, going back to the standard penetration test and taking soil samples, that we tend to focus on particle size and plasticity, right? We do a sieve analysis, we might even do a hydrometer analysis, certainly we do Atterberg limits, things like that, fall cone tests, whatever. But Dr. Robertson has been a proponent of taking a little bit different view of soil. And his work in this area has been recognized globally as the de facto standard in this regard. Dr. Robertson's work is also focused a lot on soil structure or microstructure for understanding the difference between what I mentioned previously, the behavioral age of a stratum versus its geological age, which are not necessarily the same. And I'll give you examples of both in this presentation, where they are the same and where they're not the same. Dr. Robertson has also been very generous with making his published work available. He has many publications and his own narrated PowerPoint presentations available on his personal website that you can find easily enough online. And he has also co-authored a cone penetration test user's guide that is published by Greg Drilling and Testing, which is a cone penetration test contractor in North America. And Dr. Robertson has been affiliated professionally with Greg Drilling and Testing since 2005. Now, the most recent edition of this document, at least to the best of my knowledge, is the 6th edition that was published in 2015. And again, you can find this document online as well. This also contains a very brief primer on the cone penetration test. So between this and the aforementioned NCHRP synthesis, you could get a very good practice-oriented summary presentation about the cone penetration test. So in summary, any geoprofessional can reproduce the calculated outcomes that I'm going to show you in this presentation, as well as the ones I showed earlier in my presentation on Kennedy Airport back in 2020. It takes some time and effort to go through the published information, because for many of the parameters I'll show you, there are multiple empirical correlations. It's not just that there's one way to do things. There could be 2, 3, 4, 5 different ways to calculate total unit weight, for example. So you have to do some work to look through the available information. The nice thing is that to use this information, you don't need a calculation tool any more complicated than spreadsheet software. You don't need any proprietary software or anything like that, although there is certainly proprietary software that is available for purchase. I've used some of that software. It's very nice. So you can certainly find proprietary software that will interpret the data for you. Or you can create your own spreadsheets, which I've done both. I certainly tried the proprietary software, but for many years now I have developed my own spreadsheet because that allows me to incorporate all the relationships that I feel are appropriate. Now you could, if you wanted to, do these calculations by manual calculation. These empirical relationships are fairly simple algebraically in that regard. But really, it's the sheer volume of data produced by the modern cone that really dictates an automation of the calculation. Now, for example, the earliest cone penetration tests performed at Kennedy Airport predated the piezocone. So they only measured 2 pieces of data, the tip resistance, QC, and the sleeve friction, F sub S. And they took those, recorded the measurements. Now you have to understand, as the cone is pushed into the ground, it is generating data continuously, but the typical practice is only to record those data at certain intervals. Now, back in the late 1980s, for the cone that was used at Kennedy Airport, those data were recorded every 300 millimeters, so every foot. On the other hand, today's piezocone and seismic piezocone soundings produce 3 pieces of data: tip, sleeve friction, and pore pressure. Now, with the 10 centimeter cone, typically it records the data every 20 or 25 millimeters, so about every inch. With the 15 centimeter cone, records data typically every 50 millimeters or 2 inch. So I think you can, as they say, do the numbers and see that the volume of data really can be quite large. Well, having covered the preliminaries as to why I decided to do this presentation, a little bit of a background on the cone penetration test itself, for those of you who may not be very familiar with the test and want to do some additional reading on your own, let me now get into the case history by first discussing the regional geology. You can find a good overview of the geology of the New York City metropolitan area, especially that related to Pleistocene glaciation, in my earlier presentation on Kennedy Airport. As I said at the beginning of this presentation, both Kennedy Airport as well as the site of the case history I'm talking about in this presentation, although they're about 40 kilometers apart, were affected by the exact same Pleistocene glaciation processes. Well, as noted earlier in this presentation, the soil type I'm focusing on here is Varved clay. It's a type of Pleistocene glaciolacustrine sedimentary deposit that is really, the signature is the so-called annual summer and winter cycles of soil particle deposition that produces a soil stratum that has a very distinctive visual layering. This particular specimen is from East Barnett, Vermont, in northern Vermont. And this highlights 1 year of deposition. Now you see in this case the annual cycle was about a little bit more than 3 centimeters thick, so roughly 1.5 inches. This is quite thick in my experience. I've certainly seen many Varved clays where the annual cycle was no more than a few millimeters, fraction of an inch thick. So the thickness of this annual deposition cycle can vary substantially in Varved clay deposits. And this distinctive visual appearance in vertical cross-section, sometimes you'll see referred to as rhythmic banding, because as you see, it's repeated throughout the specimen. Each one of these represents a different year, and you do see even within the specimen, the thickness of the annual cycle does vary somewhat. Now, it's typically the relatively coarser granular particles, and these are usually in the fine sand to silt range, are deposited in the summer when the water velocity in the glacial lake is somewhat greater. And the finer particles, which are typically predominantly minerals, are deposited in the winter when the glacial lakes would typically freeze over, so the water would be very, very still and kind of be like running a very large hydrometer test, if you will. Now, because the different soil particles typically have different colors, and this is due to the fact that they have different mineral and weathering origins, mechanical versus chemical, from bedrock. So typically the resulting soil has a visually distinct layered appearance as well. Now, in most cases, and this is not always, but in most cases that I've seen, the lighter colored varves, and very often they will be a light gray color, at least in the soils I've seen, tend to be the so-called winter clayey particles, while the darker colored varves are the summer silty fine sand particles. Now, for example, in the case history side I'll be talking about today, these so-called summer particles typically are very dark red or maroon in color by virtue of the sedimentary bedrock from which they were developed. Now, as I said earlier, extensive deposits of Varved clays are found in many parts of the world, certainly many parts of North America. Now, in my experience, which goes back to the 1960s when I was a student in engineering school, undergraduate, these deposits used to be typically referred to by the geological name of the former glacial lake in which a particular Varved clay deposit was created. Right? Geologists have given these glacial lakes, which typically no longer exist, names. Now, more recently, the last few decades, I've noticed a trend has been to refer to Varved clay deposits using broader regional names, as I think it's been found that in many cases, what we find in a region is that we have the collective net result of different glacial lakes that may have been at different locations or different stages of Pleistocene glaciation. And we're going to see this stage issue in a bit with respect to this case history I'm talking about today. However, the lake name nomenclature is still used to define specific areas within regions, although some of these names have changed from those used in the past. So I'm pointing this out because if you look at older literature, and this is certainly true if you look at literature, for example, here in the New York City area going back to the 1960s, 1970s, you'll see reference to glacial lakes that those names are not used in present day literature and could be a bit confusing till you sort things out. And I will give you a specific example that's relevant to the case history I'm talking about today a little bit later on. Now, in the U.S., what is referred to now as the Connecticut Valley Varved Clay in New England. And you see this on two separate graphics that I found online. Here we see New England. You see the Connecticut Valley Varved Clay is a very significant sediment deposit. Here's the Boston Blue Clay, which is probably familiar to just about everybody around the world. It's been discussed for a very long time, going back to the research of people like the late Professor Chuck Ladd at MIT and others, as well as up here in Canada, the Champlain Sea clays, the so-called quick clays that we find in the St. Lawrence River Valley, very extensive throughout southern Quebec province, a little bit of upstate New York, the United States, and a little bit into province of Ontario. And we see here that what I was talking about, we see that there are several glacial lakes affiliated with the Connecticut Valley Varved Clay, mostly Lake Hitchcock, Glacial Lake Hitchcock was the predominant one. And the focus of the Connecticut Valley Varved Clays is simply because there's been decades of research done by faculty members, geotechnical engineering faculty members, in the past at MIT, more recently at the University of Massachusetts at Amherst. And UMass Amherst is here, right smack in the middle of Glacial Lake Hitchcock. And of course, MIT is over here in Cambridge, Massachusetts by Boston. And just for reference, this is the East Barnett, Vermont location that I showed you in a prior slide, just to give you an example of what glacial Varved clay looks like. You see it was in the more northerly stretch of Glacial Lake Hitchcock. Now the Varved clays of the Hudson River Valley, that I will refer to as the Hudson Valley Varved Clays, they stretch from the Champlain Sea deposits, the so-called quick clays in the north. Okay, here's the former Champlain Sea, dominated by quick clays. Hudson Valley Varved Clays stretch all the way down about 400 kilometers to the New York City metropolitan area. And here's the Connecticut Valley Varved Clay sequence by comparisons. And you can see what I was talking about. You see how there are several Lake Hitchcock, Glacial Lake Hitchcock is but one of several glacial lakes that are now associated with the Connecticut Valley Varved Clays. So this has been one of the reasons why people have tended to use these regional names like Connecticut Valley Varved Clays, Hudson Valley Varved Clays. As we'll see, there are many glacial lakes associated with the Hudson Valley Varved Clays. But in any event, the Hudson Valley Varved Clays have been much less studied by geotechnical engineers compared to those in the Connecticut Valley, with the exception the most southerly area around the New York City area. And this is, I'm biased because I've spent my entire life and professional career based in this area. But it's extremely interesting area geologically for reasons I'll point out in a minute. Not the least of which is that the Hudson River has had multiple channels through this area over geological time. So if we enlarge this area, this is from a very nice document produced about a decade ago by Stanford, who was a state geologist in New Jersey. You can find this report online. What makes the here's New York City for reference. Right? Here's Manhattan, Brooklyn, Queens, Staten Island, the Bronx. What makes the New York City area so interesting, I think, geologically, is that the Pleistocene Epoch terminal moraines tended to go right through the area. Now, this black curve that you see here is a predominant terminal moraine of the Wisconsin glaciation. There were some earlier terminal moraines here in northeastern New Jersey. But all of these different black curves that you see are different stages of the retreating glaciers. And this is very important because as the glacier would advance and retreat, it could form different glacial lakes in different areas at different times. So here in the greater New York City area, there are many glacial lakes, and they have a very complex geological history. But really, and certainly of significant relevance to this case history, is the fact that the Hudson River has had, as I said, multiple channels over geological time. Now, this is approximately the current channel of the Hudson River, and you can actually find, even though this is offshore in the Atlantic Ocean, there's a very well-defined Hudson River canyon continues out onto the continental shelf. And this reflects the fact that at the peak of the most recent Pleistocene glaciation, what geologists refer to as the LGM, last glacial maximum, which was perhaps 15, 18, 20,000 years ago, sea level was 100, 125, 150 meters, so several hundred feet lower than it is at present. So the sea level rise has had a very pronounced effect on many processes, geological processes, geotechnical processes we see here in the greater New York City area. Now, as we'll see, of particular relevance to the case history I'm talking about in this presentation is that a much older channel of the Hudson River used to flow through northeastern New Jersey, as I show you here. And more recently, geologists have identified the fact that another channel of the Hudson River, and again, both these channels predate the Pleistocene flow, as I've shown you here, which actually these ancient channels of the Hudson River are relevant to not only this presentation, but actually the former one on Kennedy Airport. And this is why I called the presentation I posted on Kennedy Airport back in 2020, river ran through it, as literally the Hudson River used to run beneath where Kennedy Airport is at present on the shore of Jamaica Bay, which is connected to the Atlantic Ocean. Well, here's our case history site here. This is the case history site I'm talking about in this presentation. Again, these are about 40 kilometers apart. And you see it straddles the former channel of the Hudson River that used to run on the west or backside of the Palisades diabase sill that runs through here, the Palisades Ridge. So the point is that these former watercourses of the Hudson River Valley certainly only add to the complexity of the geology in the New York area. I mean, between the terminal moraines, the different stages of Pleistocene glaciation, combine that with the fact that the Hudson River has had several different channels through this area over geological time, really makes for a very, very complex geological setting. And as we'll see, very complex stress history for the Hudson Valley Varved Clays. Now, as I said, the Hudson Valley Varved Clay in the New York City metropolitan areas has really seen extensive geotechnical investigation, I would say, in the latter half of the 20th century and continuing in the 21st century, really as a result of human development. And much of this has been in northeastern New Jersey in an area that is referred to colloquially as the Meadowlands. And this is in deference to the original topography through this area that was a very massive, extensive marine tidal wetland. And again, this is the consequence of the significant rise in sea level over the last 15, 18, 20,000 years, literally drowning out these coastal areas. Now, the geological feature of the Meadowlands that is greatest relevance to this presentation is, again, this former channel of the Hudson River that predates the Pleistocene Epoch. And again, for reference, the solid light blue curve is the present-day channel of the Hudson River, and New York City is over here. Now, because the bedrock underlying the Meadowlands is relatively soft sedimentary rock, it's predominantly shale. There is some archosic sandstone that is colloquially called brownstone. If you go to New York City, you'll hear people refer to older low-rise apartment buildings as brownstone buildings, and this is simply archosic sandstone that was used as a building stone. And there are some conglomerate in places as well. These are all characterized for the most part as being a very dark red maroon color. In any event, this former channel of the Hudson River has produced a deep valley that in places as much as 100 meters or 300 feet below sea level was carved into the bedrock. And much of this valley was filled with varved clays during the Pleistocene. So it's no surprise most of the glacial lakes we find in the New York City area were once in the Meadowlands area. And typically there's a fairly thin cap of Pleistocene outwash sand on top of the varved clay, and then some Holocene organic soils on top of that. Now, even though there's been a lot of geotechnical and foundation investigation for the better part of a century now, most of this was done largely using older technology, right? Standard penetration test N values, thin wall tube sampling, conventional laboratory testing, especially for compressibility using odometer tests. Now, the work by Paul Main, Dr. Main, and others at sites within the Connecticut Valley Varved Clay, which is kind of off the map here to the right, has shown that the piezocone and seismic piezocone are really well suited for site characterization, a wide range of properties and parameters for the varved clays. And as such, the cone penetration test can supplement and complement traditional site characterization tools with the SPTN values and tube samples, laboratory testing. So there's no reason why the piezocone and seismic piezocone could not provide the same benefit to the Hudson Valley Varved clays. And that's really the thrust of this presentation, to illustrate this using a relatively recent small project case history. Well, let's get a little bit more specific now about the case history site and an overview of the project. Okay. Well, for client confidentiality reasons, I'm going to be vague about the precise location of the case history that I'm discussing in this presentation, as well as the nature of the proposed construction. I'll just say that it was a recent project within the past decade, and involved a multi-story commercial building that replaced an existing single-story commercial industrial building with about the same footprint. The case history site is located within a former floodplain of the Hackensack River, which at this point here in northeastern New Jersey. Again, for reference purposes, here's New York City, here's Manhattan, Brooklyn, Queens, Staten Island, the Bronx is up here. Here's the current course of the Hudson River. So we're in northeastern New Jersey. The Hackensack River at this point is a tidal estuary. It's connected to Newark Bay, which is connected to the Atlantic Ocean. So it has that in common with the Kennedy Airport site, in that they're both connected ultimately to the Atlantic Ocean. So at the case history site, it's only a few meters above mean sea level. And here again is for reference, here's the Kennedy Airport site that I talked about last year. And again, this is about 40 kilometers apart. Very significant difference between the two sites is that, again, this red curve here is the predominant terminal moraine of the Wisconsin glaciation, which was the last major glacial episode. So the fact that these two sites are on different sides of this predominant terminal moraine really dictate the reason why the subsurface conditions, although both of them were influenced by the glaciers, are so different. The soil stratum at the case history site that most influenced site development and foundation design was Glacial Lake Hackensack, which is part of the Hudson Valley Varved Clay system. And Glacial Lake Hackensack is a very predominant glacial clustering deposit in the Meadowlands. Again, this entire area here is referred to the Meadowlands, and you can see from the different colorations that appeared in this paper by Cheryl Moss, a professional geologist, back in 2018. Glacial Lake Hackensack once had two different stages. And again, these black curves you see here, and as well as this one that's highlighted red, these were different stages of the glacier. And this staging near the terminal moraine is what allowed these glacial lakes, in this case Hackensack, which is here, as well as down here, to have different phases or different stages, if you will. It really produced a very complicated depositional and stress history environment. Now again, relevant to the case history site is that because the Meadowlands overlies this ancestral channel of the Hudson River, at the case history site, the sedimentary bedrock, which we'll see is shale, is about 50 meters below the ground surface. As I indicated, there are portions of the Meadowlands where bedrock is of the order of 100 meters, 300 feet below the ground surface or sea level. So somewhat less here, but still a substantial thickness of varved clays were deposited, as we'll see at the case history site. And again, here's the present day. The light blue solid line is roughly the present day Hudson River channel for reference. Now, just to digress for a bit, to talk a bit further about something I mentioned a few slides back. As I said, if we go back to, say, the 1960s, 1970s, my experience, my firsthand experience, is that terms such as Connecticut Valley Varved Clay and Hudson Valley Varved Clay were not used. In New England, they talk about Glacial Lake Hackensack. Here in the New York City area, to give you an example, people talked about Glacial Lake Flushing, which is Flushing is a neighborhood of northern Queens. So we're talking about an area in this general area up here. Well, this is a very good example of what I was talking about earlier, that as part of the trend in recent decades to talk about things on a more regional basis, Connecticut Valley Varved Clay, Hudson Valley Varved Clay, along with that has come the renaming of glacial lakes. So for example, if you look at modern day geological papers, you don't see any mention of glacial lake flushing. It's not that it's not there. The remnants of what used to be called glacial lake flushing are there, but they are now lumped in with glacial lake Bayonne, which geologists now interpret was a single glacial lake that covered not only northern Queens, but northern Brooklyn, parts of Manhattan Island, northeastern New Jersey. So again, I point this out because if you're looking at doing some background geologic research about a given area, certainly here in the New York City area, you will often find reference to glacial lakes that present-day geologists don't use those names. So it can get a bit confusing until you realize that due to the last several decades of new interpretations, reinterpretations, that the definition of glacial lakes has certainly changed, and along with that has been changes in nomenclature. Now, at the time of the site characterization investigation for the case history I'm talking about here today, the overall site was quite level, less than a meter of elevation variation around the existing building. But all the borings, all the explorations for the new building had to be done outside the footprint of the existing building. Nothing could be done inside of the footprint of the existing building. Now, the site was initially investigated using a very traditional approach, 6 conventional borings, most of which went down to bedrock, cord bedrock, standard split spoon sampling, nominally undisturbed sampling using a 3-inch diameter thin wall tubes and a piston type sampler. And there's very limited laboratory testing. Again, this was a very modest project. There were 2 odometer tests, and later on I'm going to show you the interpreted or estimated yield stress values, sigma prime VM, from these 2 odometer tests. And these interpretations are ones that I did independently. These are not interpretations that were done by others who were managing this project. And I use what is called a Burmester method. This is a method I would suspect that very few of you nowadays have even heard about, no less used. Donald Burmester was, if you're not familiar with the name, was a professor of civil engineering at Columbia University in New York City. And because I got my bachelor and master degrees there, I'm very partial to his work. He was one of the earlier but lesser known pioneers in the early years of soil mechanics. And by early years, I'm talking about 1930s, 1940s, 50s here in the United States. He did not publish to the extent that others such as Arthur Casagrande and Donald Taylor, for example, published. He wrote a textbook, but it was just a very soft cover textbook. Very few copies are extant. I've never been able to get a copy of his textbook. He didn't publish. Burmester did not publish widely. He published, most of his work was published by ASTM, was formerly known as American Society for Testing and Materials. But he was one of the early pioneers, as I said, and did some very nice work. And a lot of it, some of his more important work involved odometer testing and interpretation of odometer tests. And I've found his method to be superior, quite honestly, to the Casagrande method that probably just about everybody uses throughout the world. The one downside of the Burmester method is you do need to run an unload-reload cycle in order to use it. But it is, in my experience, much more foolproof, much more forgiving, much less subjective. As we know with the Casagrande method, trying to find that sharpest point of the test curve really can involve quite a bit of subjectivity, to be kind. In any event, I just wanted to point out that the results of the odometer test were based on my own interpretation. Now, there was a supplemental investigation that consisted of 1 piezocone, referred to as CPT01, and 1 seismic piezocone, referred to as sCPT02. The cone used a 15 square centimeter area tip, and the data were recorded every 50 millimeters. And for the seismic piezocone, the shear wave velocities were obtained every meter. Now, the aggregate outcome of the 6 borings and the 2 cone penetrometer soundings indicated that within reason, the site conditions across this site, it was, again, a fairly small site, were reasonably uniform. And certainly for the purposes of this presentation, I'm going to represent them by a single geological profile. The datum for this profile, I have converted it to meters, is NAVD 88. That's the North American vertical datum of 1988. And certainly for discussion purposes, the elevation 0 in this datum is nominally mean sea level in the adjacent Atlantic Ocean. So again, you can see the site was only about 2 meters above the present day mean sea level. I'll discuss these strata on the following slide. But before I do, I just want to point out here are the locations of the 2 odometer tests that were done, both of them within the Pleistocene Varved Clay stratum. Well, let's discuss the predominant soil strata at this site. Well, to begin with, the groundwater is fairly shallow, about 1.5 meters, 5 feet below the ground surface. And this reflects the fact that the site is adjacent to the Hackensack River, but measurements indicated that it was far enough inland from the present Hackensack River so that there are no tidal effect on the groundwater level were apparent. The superficial soil stratum was some Holocene fill underlain by floodplain deposits, and the fill and the floodplain deposits were often hard to tell apart. They're predominantly coarse-grained in nature, but there are numerous layers of fine-grained soil in the floodplain deposits that were organic in nature. That's no surprise. At this site, the Pleistocene cap, if you will, of outwash sand was relatively thick in the scheme of things. It was about 10 meters, 30 feet thick. And that's substantially thicker than we find in many parts of the New York City metropolitan area. And although I'm not going to get into the foundation selection and design at all in this presentation, suffice it to say that this Pleistocene sand stratum was sufficiently thick that all of the foundation alternatives that were investigated, and this involved various types of driven or drilled deep foundations as well as some ground improvement methodologies, all of them focused on using this sand stratum as the bearing stratum. Okay, so regardless of what foundation alternative was being investigated, deep foundations to rock were not a serious consideration for such a modest building. Rock was down about 50 meters, over 150 feet. That was certainly never a serious alternative. So the reason I'm emphasizing this is because this was going to be used as the bearing stratum no matter what was selected. Clearly, the compressibility of the approximately 25 meters of Pleistocene Varved Clay were very significant, because no matter what type of foundation you installed to bear in the stratum, it was going to impart stresses on the Varved Clay. So settlement considerations of the Varved Clay really were quite significant. And again, here are the locations of the 2 odometer tests that were done. Now, the aggregate thickness of the Varved Clay at the site was, as I said, about 25 meters, 80 feet. The cones achieve refusal at the bottom of the Varved Clay. The conventional borings did indicate there was about 10 meters of very dense Pleistocene till down here, predominantly coarse grained soils, and then underlain by shale bedrock, which is the characteristic crystalline bedrock that is found throughout the northeastern New Jersey area. And this is part of the so-called Newark supergroup of the lower Jurassic, upper Triassic period. Now, I've broken the Pleistocene Varved Clay into two very distinct strata by color. And by the way, I'm going to be using the same color combination throughout the remainder of this presentation to help with understanding things. It was very clear that the Pleistocene Varved Clay, although it was nominally all Varved Clay, was very distinctly two distinct zones throughout the site. And distinction was more than the usual stiffer over softer type of consistency that we often find in Pleistocene sedimentary deposits, not just Varved clay. I mean, for example, very characteristic of other Pleistocene deposits such as the Boston blue clay, for example, where due to desiccation and other factors, you have a desiccation crust, so the upper part tends to be relatively stiff, and then it degrades down to a much softer, nearly normally consolidated zone beneath. But here it was more than that. Certainly that upper 10 meters or so with a Varved clay, substantially coarser grained than we typically find with Varved clays, quite a few sand lenses. So that in and of itself indicated very different depositional environment for this upper 10 meters compared to the lower 15 meters of the Varved clay. And these distinctions will become very, very, very clear when we look at the cone penetrometer data. Well, now let's get into the heart of this presentation, that is the interpretation of the CPT results. And as you could see, I've broken this up into several topics. This is a very substantial part of the overall presentation, this segment. And I've broken this up into different categories based on different soil properties and parameters that we're looking for. Well, just to give you an introduction overview of what we'll be covering in this segment. This presents, as I said, this is the primary focus of the presentation. It presents the combined empirical and theoretical assessments of the piezocone and seismic piezocone data solely for the purposes of site characterization. All right, I'm not going to get into foundation, selection, and design at all. This is purely a focus on site characterization. As I indicated earlier, all of the results I'm going to show were based on published empirical correlations or very simple, well-known theoretical relationships. For example, shear modulus is equal to total density times shear wave velocity squared. All of the calculations and all the plots were done using Excel, and this was intentional just to emphasize the point that you don't need anything more sophisticated than current version of spreadsheet software to do a very detailed data assessment of cone penetrometer data. So the point I'm getting at again is that all the results I'm going to show you, any geoprofessional, geotechnical engineer, foundation engineer, geologist, she or he can reproduce what I'm going to show you. Now, as I'll show in a bit, the basic QC, FS, and U2 data from both the piezocone and seismic piezocone were very similar, and for all significant intents and purposes were identical. So I'm only going to show you the detailed interpreted results for the seismic piezocone. And this is intentional to show you what is achievable just using the basic QC-FS-U2 data that you would get from a piezocone sounding, and also to show you what significant additional information can be gotten only from the site-specific shear wave data that you get from a seismic piezocone. Now, as I indicated to you a couple slides ago, I've broken things up into groups of soil properties and parameters that have the same basic theme or objective. I'm going to start off with the basics, with the raw data, and I'm going to only show you initially the relationships that you get from the basic QC-FS-U2 data that you would get from either a piezocone or seismic piezocone sounding. And then once I've done that, I'll show you what additional information can only be gotten from a seismic piezocone sounding. I do want to point out that there may be cases where you only have older cone soundings that only produce QC and FS data, no pore pressure measurements. I found that if you have a site where the soils are predominantly coarse-grained in nature, it is reasonable in most cases to assume that U2 is equal to U sub O, the static or overburden water pressure. So you kind of, point is you can create, if you will, fictitious U2 data by assuming it's equal to the static water pressure. And I've done this successfully using some of the early cone penetrometer tests done at Kennedy Airport in the 1980s. And this was done to enlarge my database of site characterization for research I've done related to taper piles at Kennedy Airport. But you do have to use some caution if you're going to use this interpretation. I do want to point out that, of course, for the older cones, that the Q sub T, which is the notation for corrected tip resistance, Q sub C, the notation for uncorrected tip resistance, are the same, as there's obviously no pore pressure correction to be made because there was no pore pressure sensor. So let's start at the very beginning, talking about the basic data that you would get from a cone penetrometer sounding and some of the more modern normalization concepts that we're using nowadays. Let me just say initially that I'm going to show you for these first few slides that I'm going to present the data as continuous line segments. This is the traditional way that you see cone penetrometer, not only the raw data, but also the interpretations presented. Right? If you look at any of those research reports or design manuals that I mentioned earlier, you look at published papers, it's very typical that not only the raw data, but the interpreted data are presented as continuous curves. And I'm emphasizing this because I'm going to show you an alternative way of data presentation in a bit and explain to you why I sometimes, well, nowadays I always use that alternative interpretation as well. There's benefits to, my point is there's benefits to different ways to portray these data when we're plotting. So let's start off with, this is Q sub C. This is the basic measured tip resistance. It is what we call the uncorrected tip resistance. We now realize that when we have a piezocone or seismic piezocone, that because of the pore pressure sensor at the U2 location just behind the tip, that we need to make a correction for the pore pressure acting behind the tip. Now, for terrestrial soundings, the difference, as you could see, is really, it's hard to tell. There is a difference. Much greater difference if you were doing a sounding in open water. There, the corrected tip resistance is quite a bit different, or can be quite a bit different from the measured or uncorrected. I emphasize this because you do want to pay attention If you're looking at empirical correlations, things like that, a lot of the older empirical correlations used Q sub C, the uncorrected. Nowadays, we almost always use Q sub T corrected. As I said, for the older cones that did not measure pore pressure, these are the same inherently. As I'll talk about a bit more later on, nowadays we always normalize the data. And the most common modern normalization parameter is capital Q sub Tn. And the normalization is basically done to basically correct for overburden pressure effects, vertical overburden pressure effects, pore pressure effects as well in some cases. So what this does is to eliminate the effects of confining stress and focus on changes in the material. That's the whole logic behind normalization. More recently, there's a parameter called QTN-CS that is called the clean sand equivalent. And this is basically so that if you have for example, a siltier sand, that this empirically corrects the result to, if this were a clean sand, it would have this value. This tends to be most important for seismic liquefaction purposes. And in fact, this green line is the QTNCS 70 line. I emphasize this because if you look at some recent papers by Dr. Main and others, that this is one of many different thresholds that has been proposed for seismic liquefaction purposes, meaning that if QTNCS is greater than 70, that the soil most likely will not liquefy. If it's less than that, then there might be a potential problem. So the so-called clean sand equivalent is really something, it's a more recent parameter that's been developed primarily for seismic liquefaction related issues. Well, as I said, I'm going to be showing from here on in this overlay of the three main strata, the Holocene, fill and floodplain deposits, the Pleistocene outwash sand cap, if you will, and the Pleistocene Varved Clay in its two very distinctive zones. So I'm going to be carrying through this color scheme throughout the rest of the presentation. And we begin to see, even at this early stage, focusing on the Varved Clay, that there really is quite a distinction. We could see that in the normalized tip value, that this upper 10 meters, much greater tip resistance in general, normalized than this lower 10 meters in this case. I should add there's another 5 meters to the Pleistocene Varved Clay, that the seismic piezocone went down to a depth of 35 meters, whereas the piezocone went down to 40 meters. So in all of these plots that I'm going to show you, or most of these plots, there's another 5 meters of Pleistocene Varved Clay, but it is essentially very, very similar behaviorally to this lighter red shade of the lower Varved Clay I'm showing you here. Moving on to sleeve friction, F sub S, here's the measured values. Friction ratio, R sub F, which we've been using for a very long time now. Measurement of sleeve friction dates back to the early 1950s, to the so-called Begeman cone variation. And so we've been using this friction ratio for many, many decades now. The normalized friction ratio is a more modern development. And certainly you see how the Pleistocene sand stands out compared to the Varved Clay, for example. And finally, with the pore pressure, the U2 pore pressures, here's the measured value. And on all of these plots, I do show you the U sub O, the overburden pore pressure as a solid continuous blue line. And the dark red curves are the measured pore pressures. Here's the measured value. We can manipulate pore pressure data many ways. One common way is to plot a head difference. Another is to plot capital U star, which is a very common normalized value. B sub Q is another normalized variation. You can see the equations are up here. B sub Q is mostly used for fine-grained soils. You see, certainly with the Pleistocene sand, BQ is 0. But no matter how we portray the data, again, you can see, and I want to focus on this part, that the two zones, the upper and lower zones of the Pleistocene Varved Clay are very, very different in their pore pressure behaviors. And one of the things that pore pressure measurements give us is a dividing line between dilative and contractive behavior. And here we're talking about volumetric behavior under shear. Dilative, of course, is volume increase. Contractive is tendency for volume decrease. And I've just labeled these so we could see which is which on these different data portrayals. From time to time, for some of these early slides, I'm going to show you a comparison between again, I'm focusing mostly on the seismic piezocone, but I will show you some comparisons to the piezocone sounding, just to verify a statement that I made earlier, and that is that the two results were, for all practical purposes, identical. So what you see here is the dark red curve is the seismic piezocone that I'm focusing on. The green curve is the piezocone. And please note that I've changed the vertical axis from depth to elevation. And on these comparison slides, I did that on purpose because there's a slight, I believe it was about 500 or 600 millimeter difference, about 1.5 feet or so difference in elevation between the two cone soundings. So I wanted to portray them with an equal basis. So I've, again here, using the NAVD88 datum. So here's the normalized tip, the normalized friction, the absolute pore pressures, and the normalized water pressures. And you see that, except for a little bit of variation in places in the Holocene fill and floodplain deposits, as you might expect, that for all practical purposes, the two soundings gave identical results. And as I said, you do see that the piezocone sounding did go down another 5 meters till it met refusal at the top of the glacial till. So again, this is just verifying that the two cones basically gave the same results. So whatever interpretations I show you for the seismic piezocone, I think you could feel that the same, very similar interpretations would come from just the piezocone sounding. Well, let's now move on to soil identification and soil behavior type categorization. For most of the 20th century, during the early development and evolution of the cone penetration test, it was natural that the primary goal was to develop empirical correlations that would mimic conventional soil type identification, which, as I said earlier, has always been based on soil particle size and plasticity, right? Because this is what we get from physical samples, sieve analysis, hydrometer test, Atterberg limits, fall cone test, things like that. So as I said, it was logical we do this because it's just a carryover from what we had always done since the beginning of modern soil mechanics in the 1920s. Well, These CPT-based soil identification correlations, no surprise, have gone through many, many stages of development over the years. Earliest ones date back to the early 1950s when the friction sleeve, sometimes in the early literature was called an adhesion jacket, was developed. And this was the so-called Begeman cone, after the person who developed the friction sleeve. And you see this was just the tip resistance, uncorrected, corrected the same, obviously, in this case, versus the friction sleeve. Moving on another 3 decades, Robertson and Campanella in the 1980s developed a correlation, and this is one of the best known of the later generations of correlations, and I still see people use this to the present. Notice that this is based on the corrected tip resistance and the friction ratio. But if you had an older cone with just QC and FS data, you could still use this. All right, that's the nice thing is that, and by the way, just mentioned in passing, when you look at a lot of these older correlations, you will very commonly see the stress unit of bar that is used. If you're not familiar with that, 1 bar is 100 kilopascals, which is approximately 1 atmosphere, right? 1 atmosphere is like 101 kilopascals and change. But whether it's the older Begeman correlation or the Robertson-Campanella correlation, the attractive thing is that they're usable with the older cones that only produce QC and FS data. Certainly you could still use them with piezocones and seismic piezocones, obviously. But I still see people use this correlation to the present. There's a lot of people who still prefer that classical, traditional type of soil identification. Well, as I said earlier on, one of the things that Dr. Peter Robertson has really become known for is promoting the trend away from traditional soil identification and what we call soil behavior type, SBT. And the logic behind soil behavior type concept is that the cone penetrometer is better suited to defining soils by their mechanical or performance-based characteristics such as strength and stiffness, as opposed to their physical characteristics of particle size and plasticity, as we've done with conventional site characterization methodologies. You know, and given, if you think about it, in geotechnical and foundation engineering practice, we're after the mechanical behavior of soil, not its physical particle size per se. So the soil behavior type categorization is arguably more useful than just focusing on particle size and plasticity. Well, in the 30 or more years since Robertson first proposed the soil behavior type correlation or concept, no surprise it's gone through quite a bit of evolution and modification. So I point this out because you really need to be very clear about which particular version of the soil behavior type concept you're using. And I emphasize this because I found that the terminology and the notation, unfortunately, are not always consistent in published work, even by the same author. I've seen situations where the same author is called the same thing, different terms, use different notation in different publications. So you really need to pay attention to the specifics when you're using soil behavior type. Well, the original soil behavior type concept was introduced in the 1980s before the piezocone was widely available. So it was based on just the QC and FS data that you got from a normal, the older cone penetrometers. And while the original version of the soil behavior type concept has as many as 12 categories, or what we call zones, this eventually evolved to a 9-zone categorization, and this should be very familiar to you. You see this 9-zone categorization still used by a lot of people to the present time. Although, as we'll see, how these 9 zones are defined has gone through some change. This original 9-zone variation that was just based on tip and friction sleeve data is what we call a non-normalized soil behavior type categorization. And the reason for that will become clear in a sec. Well, we've since moved on to what we call normalized soil behavior type, and is usually given a lowercase n at the end to indicate normalized, but not always, right? So you do need to be careful. A lot of publications, this n will be left off. You need to look at how the axes of the plot are labeled. And you see here normalized tip resistance, normalized friction ratio. So always pay attention to the axes, not so much the name, not so much the acronym or initials that are used. Now, the original normalized chart kept this 9-zone categorization of the non-normalized chart, but it introduced a new parameter called capital I sub C, that is called the soil behavior type index, and I sub C of 2.6 has been adopted as the dividing line between coarse and fine-grained soils. Right? And you see that shown here, and you see it as well. I've highlighted it in the table here. Now, this is very, very important to remember, because as I'll point out and discuss further in the next few slides, this I sub C parameter, actually it's a little bit more modern variation, is really the cornerstone of a lot of the empirical correlations. The point being is that in these empirical correlations, if I sub C is less than 1, the implication is that it is a coarse-grained soil, and a coarse-grained soil correlation is used. If I sub C is greater than 2.6, I think I said 1 by mistake, I'm sorry. If I sub C is less than 2.6, then it is assumed to be a coarse-grained soil, so coarse-grained soil correlations apply. If I sub C is greater than 2.6, it's assumed to be a fine-grained soil, and fine-grained correlations apply. So I point that out because we'll see some what may appear to be curious results shown subsequently. Is the result of I sub C really being the central feature of many empirical correlations we use nowadays for site characterization. Now, initially, I sub C was based on a normalized tip resistance you see variously called Q, Q sub T, Q sub T1, 1 meaning the normalization stress, sometimes with a Q. So you might see lowercase q sub T sub 1. In recent years, Dr. Robertson has proposed using a modified normalized soil behavior type index, I sub Cn, that is based on QTN. Again, QTN is really the current thinking in terms of normalized tip resistance, as well as a dimensionless exponent n that can vary between 0 and 1. And by comparison, the original I sub C, the original normalized soil behavior type index, implies that n is constant equal to 1. Now, this new modified normalized soil behavior type index takes a bit more computational effort than I sub C, because you need to go through an iterative calculation, because QTN, N, and ICN are all interrelated algebraically, but really this is trivial computationally when you use a spreadsheet or other calculation software for the calculation process. So this is not, to use this current thinking ICN is really not a burden in my experience. Unfortunately, publications that I've seen are not always clear and consistent with notation. I've said this about soil behavior type, SPT, SPTN, and that's true with I sub C and ICN. So there are cases when I sub C appears, yet what is intended is ICN. You really need to pay attention to how the parameter is defined in that paper. Now, as Robertson noted, the largest differences between IC and ICN tend to be for coarse-grained soils, and I'll show you how things look for the case history site in a second. And the reason I'm spending time emphasizing this is, again, whether it's I sub C or ICN, these have emerged as key parameters for the interpretation of cone penetrometer data, not only in their own right for defining normalized soil behavior type, but you find I sub C and more recently I sub CN in numerous empirical correlations for soil properties and other soil parameters. And again, whether it's I sub C or I sub CN, this 2.6 is always the magic value, if you will, for defining whether something is nominally coarse-grained in its behavior versus nominally fine-grained in its behavior. So that's why I'm emphasizing this discussion of I sub C and I sub CN. It's really emerged as being a really crucial parameter in interpreting cone penetrometer data. Well, as I said, this whole soil behavior type concept has been evolving since the 1980s, and the most recent evolution focuses more explicitly on mechanical behavior that is broadly divided into contractive versus dilative. And again, a lot of this is driven by the use of the cone penetration test for assessing things such as seismic liquefaction, where contractive and dilative behavior plays such a prominent role. So what you see here, and this is from one of Dr. Robertson's publications, superimposed on the traditional 9-zone SPTN chart, is showing this curved dividing line between dilative behavior and contractive. And then this is further broken into drained. In some cases you see it called drained, some cases you see it called coarse grain, some cases you'll see it called sand-like. These all mean the same thing in this context. Versus undrained or fine-grained or clay-like behavior. So for example, the C here means coarse grain, dilative, fine grain, dilative, fine grain, contractive, coarse grain, contractive. And there is a transitional zone. Okay, although this magic value of 2.6 that goes through here is used as an absolute dividing line in formulas or empirical relationships, in reality it's recognized that there is a transitional zone. Well, along with this process, the number of behavioral zones has decreased from 9 to 7. So the current normalized soil behavior type really has 7 zones, not 9. Although I have to say that looking at even very recent publications, I find that most people other than Dr. Robertson are still using the 9-zone charts. But as you'll see, I have embraced the 7-zone chart as well. And so this just shows the new 7-zone chart superimposed on the old original 9-zone chart. I'll show you results from both for the case history site in a minute, but I will be focusing on the 7-zone chart. Okay, having discussed the concept behind soil behavior type index and related parameters, let's see how this is applied to our case history site. Now, before I get into things, I want to point out what should be visually obvious, and that is I'm tending to switch to portraying the results as individual data points as opposed to continuous curves. And there's a good reason for this. I will defer that discussion of the reason to a little bit later when it makes a little bit more sense as to why I've done things the way I've done. Well, let's start out first by comparing IC and ICN. As I said, they do give you a little bit different results, primarily in the coarser soil, but the differences tend to be small. I always calculate both values so I could look at them and compare them. Very often the difference is in the second decimal place, so it tends not to be terribly significant. Here's a plot of ICN versus depth superimposed on generic soil type categories. We haven't abandoned the traditional soil descriptions completely. We just don't focus on them nearly as much as we used to. And again, the solid green line here is the magic value of ICN of 2.6, which is the dividing line between the finer grain soils and the coarser grain soils. And again, with these plots, we now really begin to see the value of the piezocone, the size of piezocone, as opposed to traditional soil sampling. In this case, we're getting data points every 50 millimeters, every 2 inches. So for each one of these 5-meter increments of depth, we have 101 data points. So we're getting a lot more data. And really, this wealth of data is what allows us to detect these nuanced variations and transitions. And you see, for example, the Pleistocene sand, outwash sand, very definite, fairly homogeneous. The lower Pleistocene Varved clay, fairly homogeneous, but we see this upper 10 meters of the Varved clay really very transitional in its nature. And this is also apparent in this N parameter that we use for ICN. Again, for I sub C, this N parameter would be uniformly 1. But we see the value of this ICN is because it uses this coefficient or exponent N, which is not always equal to 1. It's less than 1 for coarser soils. But notice, again, the transitional nature of this upper 10 meters of the Varved clay is very significant. This is a correlation for the percent fines, that is the -200 material, based on IC or ICN. My experience for using this at many different sites is I calculate this. Do I put a lot of faith in the results? Not always. I think it's one of the poorer correlations at this point for cone data. That's not to say that we could not improve upon it in the future, but I always look at this take it with a grain of salt, as they say. Well, moving on to the soil behavior, normalized soil behavior type charts, this is the original 9-zone variation, and we see the variation in zones with depth. Again, very clearly the transitional nature of this upper 10 meters of Varved clay. If we go to the more modern current 7-zone version, again, we see the variation with depth. However, with this 7-zone version, I prefer to show the results on a plot of this type. And again, this is the dividing curve between dilative and contractive. This is the more sand-like coarser. This is the more clay-like finer, the transition zone. And this is the special sensitive clay category here. So what I like to do is to, when I've divided a site stratigraphy into strata, is to look at the results individually on this type of plot. So for example, the Holocene fill and floodplain deposits all plot up here, mostly dilative. We do see some clay ear zone data, and this would be where we had the organic clay layers. we see that the outwash sand, the Pleistocene outwash sand, very tightly plots in the sand dilative category. Interestingly, this upper 10 meters of the Varved clay, the stiffer Varved clay, you really see it plots in the dilative zone for the most part, but you really see the transition from sandier to clayier type of behavior. Again, this is really behavioral more than hard and fast type of soil particle size per se. Whereas for the lower portion of the Varved clay, very definitely in the contractive zone, a lot of it clustered in the sensitive special CCS zone down here. This is what I'm emphasizing, which as we see, I'll bring back the plot I just showed you on an earlier slide. This is really a zone down here. It's about a 4 or 5 meter zone around a depth of 30 meters. And this is going to, I'm emphasizing the zone down around 30 meters because it's going to show up repeatedly in some of the later slides with a certain type of behavior. But if we plot the two Pleistocene Varved clay zones together, we really see that they are certainly not homogeneous. And this brings up a very important point I'm trying to make, and that is when you're dealing with Varved clays, all Varved clays are not created equal. The Hudson Valley Varved clays are not the same as the Connecticut Valley Varved clays, and even within the Hudson Valley Varved clays, it is very location specific. This happens to be what we see in this particular part of Glacial Lake Hackensack. I won't show you the results, but I've done a lot of work in the meadowlands, and there are other parts of the Glacial Lake Hackensack where we have very different types of observations. So the main point I want to get across here is never lump Varved clays together as a homogeneous type of material, even within the same glacial lake or within the same region, Hudson Valley Varved clays. They're really going to vary tremendously from site to site, given the depositional and stress history of the site, and you need to look at them in that context. Well, if we plot all the results from all the strata together, we see that we certainly do have quite a bit of variation throughout the site. Well, let's move on now to index properties. And again, as you see, I'm showing the data as individual data points, not as continuous curves. This is total unit weight. There are many correlations for total unit weight. I've lost track of how many. It's probably 3, 4, 5 at this point in time. I tend to calculate them all, and usually I use an arithmetic, a simple arithmetic mean, a simple basic average, mathematical average, arithmetic average of the data. And by the way, in many of the correlations for other soil properties and parameters using the cone, you need an estimate of soil unit weight or soil density. Now, it's very, very common for people just to assume a single value of unit weight or density in these correlations. I tend to use the actual values that I've calculated. It's a little bit more work in terms of, well, Excel is doing all the work, but it's a little bit more complex when you're setting up a spreadsheet to evaluate the data. But I try to use the specific values of unit weights or density that I've calculated. Here's a plot of water contents versus depth. Again, my experience, usually reasonably reliable, but it is not one of the more reliable correlations in my experience. Relative density versus depth. And I should point out, here's a case of, obviously we know that relative density is the consistency of only a coarse grained soil. So at this site, strictly speaking, it would only be appropriate or relevant for the Holocene stratum and the Pleistocene sand cap. Why do we see results, especially in this upper 10 meters of the Varved clay? Well, the empirical correlations we have for relative density are based on this magic value of 2.6 for I sub C or I sub Cn. So when you set up your spreadsheet to do the calculations using a filter of IC or ICN to decide which empirical correlation to use, if it's greater than 2.6, you're going to use the coarse-grained correlation. Well, it just so happens that especially in this upper 10 meters of the Varved clay, at a number of these data points, we had a value of ICN greater than 2.6. So we get a calculated value of relative density. Is it relevant here? No. But I'm just explaining why it is showing data points here. Similarly, this is the critical state soil parameter psi, which is a indicator of, again, the consistency of the soil. And a value of 0 is the dividing line between contractive and dilative behavior. And this is a theoretical dividing line that comes out of critical state soil mechanics. Now, a lot of times you will see people use a negative 0.05 as the dividing line between contractive, dilative. I think this is done to be a little bit conservative because one of the more common uses of this parameter nowadays is for assessing the seismic liquefaction potential of a coarse-grained soil. So, you know, you want to be a little bit conservative in making that judgment call. I've become a fan of this value largely due to the work of Dr. Peter Robertson. He's made a very convincing point that this critical state soil parameter psi is a much better metric for the consistency of coarse-grained soils than relative density. So I emphasize that because a lot of people still tend to focus on relative density, but this is a much better metric, in my opinion, and in the opinion of a lot of other people, than relative density. What I've done here is to, as I'm sure you know, Excel does not like to generate plots where an axis goes from positive to negative, from left to right. So this, I simply use some other software to make a mirror image of the plot. What I'm trying to show you here is that, of course, relative density goes from looser to denser. With the critical state parameter psi, as you go from positive to negative, you go from looser to denser. So I'm trying to compare apples to apples here. I'm showing you that the same pattern of behavior that we observe for relative density, we observe for this state parameter psi. So, but again, this is much more theoretically rigorous parameter to use to assess the consistency of a coarse-grained soil. We should be using this instead of relative density. Well, let's now talk about fluid flow. The most general empirical correlation for fluid flow properties is between ICN, the coefficient of permeability K. It applies to all types of soils. And again, you see I'm sticking to the plot of just showing individual data points, as you see with the red circles I've plotted here. Now, when you perform a cone penetrometer sounding with either a piezocone or seismic piezocone, you can run what are called pore pressure dissipation tests. And this is typically done, as you know, you run the cone penetration test by pushing the cone for generally in increments of a meter. Then you've got to put on an additional piece of rod. When you pause to put on the additional piece of rod, you can monitor the pore pressure in the pore pressure element, the U2 value. Now, generally, these dissipation tests are used to calculate or to estimate the horizontal coefficient of consolidation, C sub H. In some older publications, you'll see people call this C sub H sub H. Nowadays, we tend to just call it C sub H. You can also use pore pressure dissipation data to evaluate coefficient of permeability. And I show you that here. There were several pore pressure dissipation tests performed for both the piezocone, the size of piezocone soundings at the case history site. And I'm just showing you the results from the seismic piezocone. These are the green squares, and you can see, I've just highlighted one of them, you could see that they correlate very, very nicely with the data we get from ICN correlations. Now here's the C sub H values, and I want to point out the units I'm using here are meter squares per second. I like to use fundamental units when I use SI units, when I use metric units. That's why I portray permeability in meters per second. I know that there are decades and generations of geotechnical engineers like to use centimeters per second for permeability. A centimeter is a deprecated unit in SI. So if we're going to use SI, let's go all the way and use it correctly. So that's why I use meters per second here. That's why I use meters squared per second here. A lot of plots you'll see for C sub H from dissipation tests in the literature, they use centimeters squared for some other unit of time, minutes, hours, something like that. I think that's so that they wind up with values that are greater than 1. It makes it quote unquote nicer to plot, if you will. But the main thing I want to show you here is that, or point out here, is that the values of C sub H that I calculated from the dissipation test, these are all 1 to 3 orders of magnitude larger than typical values for fine-grained soils that you see in the published literature. And I think this brings up something that people who have worked with varved clays have always felt, and that is because the varved clays can contain all these countless very thin horizontal layers of fine sand or silt, there's always been a feeling that these kind of act as a horizontal, to increase the horizontal drainage in conventional consolidation or reconsolidation, recompression. And I think that's what we're seeing here, is that because of these countless horizontal layers of fine sand, that the horizontal coefficient of permeability of a varved clay deposit tends to be much greater by 1 to 3 orders of magnitude than you would think for a normal homogeneous fine-grained soil. And by the way, I should comment on this well-behaved zone that's superimposed on this plot. This actually relates to something that I'll talk to define in a later slide, so don't pay, I'll define this later on. Well, let's now talk about stress state, which I think is really one of the greatest benefits we have of using the cone penetration test. It really enhances our ability to estimate stress state in all types of soil. Now, before I look at the results for the case history site, there are 2 foundational topics I want to discuss. And by foundational, I mean it in the sense of fundamental, not in foundation in the context of civil engineering. So there's 2 essential or topics I want to discuss first in a qualitative sense. Number 1, and I've shown you this plot of ICN versus depth previously, because the modified normalized soil behavior type index ICN has emerged as really being a key parameter in its own right, it's increasingly used as part of empirical relationships that define other soil properties, empirical parameters. And I noted this in some of the prior slides when I said, you know, this is why we get estimates of relative density in the Varved clay, is, well, some of the data points in the Varved clay, at least at upper 10 meters, indicated a coarser nature for that particular zone. So I sub Cn was greater than 2.6, which, as we see, is less than 2.6, which is indicative of a predominantly coarse-grained soil. I'm bringing this up again here because related to stress state is an empirical parameter M prime that Dr. Main uses as an exponent in a number of his empirical equations for yield stress. And yield stress is the term I use, the notation sigma prime sub Vm. I just point out, of course, yield stress has had many different names over the years. Pre-consolidation stress, pre-consolidation pressure, maximum past effective stress. I could go on and on. Similarly, it's had many, many different notations. I use sigma prime Vm. If you look at some older publications, we use a bar instead of a prime. In Dr. Main's publications, he tends to use the notation sigma prime sub p. So you have to be careful. There's been many names, many notations, all mean the same thing. But M prime depends on ICN, and I'm just showing you, here's the variation of this exponent M prime as a function of depth for our case history site. And it's very interesting to see, again, very homogeneous values in the Pleistocene sand stratum, relatively homogeneous values in lower Varved clay. This first 10 meters of Varved clay, much more transitional, and with quite a bit of indication of soils that are sand-like in their behavior. Again, this really, to me, shows the power of using the cone penetrometer as a site characterization tool. You're getting data points, in this case, every 50 millimeters, every 2 inches. You're not just looking at a soil sample every 1.5 meters or 5 feet. So the volume of data, the ability to detect these transition type of zones as we have at this site, very, very significant, I feel. Well, the second foundational point or issue I want to bring up is that both Doctors Robertson and Main have made clear in their published work that the many different empirical correlations they've developed for site characterization using the basic QC FSU2 data from a piezocone or seismic piezocone sounding are valid for what is often referred to as a normal soil. And you'll hear them use see them use terms like young or well-behaved. Dr. Main has used colloquial terms such as hourglass sands and vanilla clays. Essentially what they're talking about is soils that are behaviorally in the mainstream. And this is very important to understand, that when you're going to develop empirical correlations, you have to be very clear about the database of soils that you're using. So because most of the soils, whether coarse or fine-grained, have this normal or mainstream behavior, it makes sense to develop correlations based on these types of soils. So, but normal in this context is broadly defined as soils that do not have structure or microstructure due to aging, cementation, or some other natural effect that is related to time as well as the environment. The groundwater chemistry. Is it fresh water? Is it salt water? Was it salt water that is now fresh water, for example, as we find with quick clays? This is all very important to impacting the structure and microstructure of the soil. And normal soil is also, in the context of fine-grained soils, what we call insensitive. Well, I'm emphasizing this because when we use these empirical correlations, we need to understand that there are certain assumptions that are built into these correlations. We need to be very clear about understanding these assumptions, in this case of normality or of behavior. And also to understand a lot of Dr. Robinson's work has been to define soils that have some structure. And as we'll see, the only way to define soils that have structure is to use site-specific shear wave velocities, V sub s, that can only be measured in a seismic piezocone sounding. So this is building up to a point that I want to emphasize, that if you're going to do cone penetrometer soundings nowadays, you must do at least one seismic piezocone sounding. I mean, that sounding is going to give you your QCFSU2 data anyway. It's going to give you your pore pressure dissipation data if you want it. But only a seismic piezocone can give you site-specific shear wave velocities. And this is really essential to properly calculating the linear elastic small strain shear modulus. And I'm going to tend to use the notation Gmax, which is the more common notation in the United States. Understand that G sub O or G naught, G0 is the more common notation outside the US. So G max and G naught mean the exact same thing. So we'll see later on that structure in soils is generally correlated to the stiffness of the soil skeleton, which is what the shear wave velocity measures and what G max or G naught reflects. So the point being is that really the size of piezocone is an essential in situ testing tool for evaluating soil structure. It's a necessity, it's not a luxury. I think there was a time not all that long ago, and I think some people still think it, that a seismic piezocone is the proverbial Cadillac that, yeah, it's nice to do, but I don't need to do it. In my experience, you need to do it, and I hope to show you some examples of why you need to do it. It's a very small increment of cost. I mean, it's going to give you your basic data anyway. Now, Dr. May's work related to structures in recent years has focused primarily on fine-grained soils. A lot of Dr. May's earlier work was on coarse-grained soils. He's given us some essential correlations for coarse-grained soils that we continue to use to the present. But his later work in recent years with his graduate students and colleagues has focused on fine-grained soils. And so since he's focused on the structure of fine-grained soils, he's taken a little bit different approach based on the QCFSU2 data that you get from either a piezocone or seismic piezocone sounding. So he's developed 3 different equations for yield stress in fine-grained soil to evaluate whether that soil is behaviorally vanilla in his terminology or not. So here are Dr. May's 3 equations for yield stress in fine-grained soil. And I just want to note that in older publications, you'll see this 0.53 is 0.54. Now for normal, well-behaved, and sensitive, quote-unquote, vanilla clays, these 3 values of yield stress that you calculate at a given depth will be approximately the same in magnitude. And he's also observed that in organic clays, you tend to have a certain hierarchy where they're not the same. And for sensitive clays, there's a little bit different hierarchy that is not the same. It just involves switching these 2 equations. Now, using this hierarchical structure, there was a site in the Connecticut Valley Varved Clay in Hartford, Connecticut, that Dr. May found to be normal and well-behaved. And actually, he talked about this site in a presentation he gave back just about 2 years ago in the fall of 2019 at a Connecticut Society of Civil Engineers section, ASCE, seminar on site characterization. I was fortunate to attend that seminar, and you should be able to find his presentation slides on his website. Now, when we apply these equations, these three equations, to our case history site, well, we get some interesting results, to put it mildly. Now, up here, we have a hierarchy that is typical of organics clays, and that's not surprising, because where we do find fine-grained soils in the Holocene, fill, and floodplain stratum, they're organic. So this is not surprising. We would have expected this. The big surprises to me were down here in the Varved clay. We have a very limited zone of maybe 4 or 5 meters around a depth of 30 meters that falls in the well-behaved category, where all three equations give pretty much the same estimated value of yield stress. But you see throughout the upper 10 meters of the Varved clay, and even through a good portion of the lower Varved clay, much more scatter in the results. The trends we tend to see, interestingly enough, really are typical of organic soils, right? The light blue, lowest, dark red in the middle, purple the highest. But trust me, these are not organic soils. These are very inorganic Varved clays. But the point still is, except for a very limited zone here, this well-behaved zone, we have indications of very non-vanilla type clays. Well, let's now look at the yield stress in a little bit more detail. First, let me look at the results based on this M prime exponent, which is applicable to all soils. Now, these three plots all show the same thing. We have the brown line is my calculation of the vertical effective overburden stress, and this is based on the static water pressures, and it is based on the calculated values of total unit weight. Okay? The red data points represent the empirical values of yield stress. Now, the difference between these three plots is that this shows all the data points individually. In this plot, what I've shown is a running average. And for the average, I arbitrarily, for each average, I use the value at a given depth plus the values 150 millimeters above and below that point. So each one of these represents an average of 7 data points over a total distance of 300 millimeters or a foot. So this is the arithmetic average, and this is the median. Right? So this is the arithmetic mean. This is the arithmetic median. So a little bit different manipulation of the same data, but again, a median over plus or minus 150 millimeters. Why do we do this? Well, this was, I can't take credit for this. The median approach was actually suggested to me by someone who's done quite a bit of work with the cone penetrometer, working for a commercial firm. And this is a technique that has been found useful in situations where the data exhibit, or the calculated results exhibit, a lot of scatter, and which they certainly do here in the Varved clay for the most part. We see very tight data here in the sand, very tight data in the well-behaved zone here. Most of the Varved clay, quite a bit of scatter. So the reason for the averaging, I thought I would try just to see how that produced. The median, as I said, was suggested to me. So these are simply 3 portrayals of the same data. The reason for using averaging or calculating medians is to try to remove some of the scatter. This last one, again, we've seen this already. This is just Maine's correlation that is applicable to fine-grained soils. Well, if we step back and look at things, we see that the conclusion I draw from this is that if we look at some of the averaging and the median calculations, we do seem to have a reasonable trend of indicated yield stress, but it's very clear that there are some, these are not just bad data. I don't think of these as bad data. It's very clear that we have some zones where, for whatever reason, now whether it was due to temporary desiccation or some other feature during the Pleistocene or after the Pleistocene, I don't think we could ever know for certain. But we do tend to have some zones where we have locally higher values of yield stress. We do notice down here where Maine's 3 equations for yield stress in fine-grained soil produce essentially the same result. These same results actually do match the results we get using this M' exponent correlation. So we would consider these results in this quote-unquote well-behaved zone. As we can see, if you look at the numbers, these vary from like 400 to 600 kilopascals. Appreciating that these have different scales, you see that they do vary from about 400 to 600 kilopascals. Right? So these, within this well-behaved zone, all of these estimates from 2 very different approaches for yield stress are pretty good. Outside those zones, we have to be careful. And this is what I was saying about you need to understand where these empirical correlations come from and what they give you. So I would tend to be careful. I would discount a lot of these values outside the well-behaved zone. I am not discounting these values here. And I'm going to illustrate why I don't discount these values in a minute. But before I do, I want to just talk a little bit about plotting choices. Okay, you've been very patient waiting to understand why did this person change from showing me continuous lines to individual data points. What's going on here? Well, there was a reason I did this, and I'm going to explain the reason because the yield stress actually illustrates it very nicely. These are the same 3 plots for yield stress. Individual data points, averaging over plus minus 150 millimeters, median over plus minus 150 millimeters. So these are the same yield stress, but now shown in the traditional way that you see it in research papers, other publications. As I say, people typically portray, whether it's the raw data obtained in a cone penetrometer sounding or the interpreted data, people almost always portray those data as continuous curves. And that works out well in a lot of cases. I mean, for example, here through the Pleistocene sand, I mean, this is pretty easy to understand. But when you get down here to the Varved clay, well, it becomes a little less clear. Well, obviously you got a data point here, and you got a data point here, and the Excel spreadsheet just connected those data points. Well, what do we have in the real world? Is it just 2 data points with nothing in between? Or do we have some smooth variation of data points in between? Now, the averaging and the median plots, they take a little bit of the scatter out, but they don't eliminate the scatter. They still leave us wondering, do I have an average data or median data here, median data there with nothing in between, or continuous values in between? The point I'm getting at is when you plot those same data as individual data points every 50 millimeters, I think it's more insightful in a lot of cases. Because if you look at the density of the data, it gives you, I think, a better feel than looking at continuous curves as to what's going on. And especially when you look at the averaging or taking the median values, again, it's pretty clear that, okay, yes, this is a general trend of yield stress, but clearly something is going on here geologically. These are not just bad data points. There's something that these higher values of yield stress are probably correct to some degree. And I'll show you the two plotting continuous curves versus individual data side by side, and just kind of let you look at this for a minute and you see what I'm getting at. That to me, I think in certain situations, especially when you have a lot of scatter to the data and you've got to give some thought to things and not just use the numbers at face value, that plotting the individual data points, I think, gives you a little bit more insight as to what's going on as opposed to the curves. Now, of course, it's not either or. I mean, in fact, with Excel, plot it both ways. And in fact, that's what I do. I've had an Excel spreadsheet for evaluating coimpenetrometer data for several decades now, and it's gone through I don't know how many variations. I used to say, this is version 7, this is version 8, and the version numbers got to be so high, I just said forget it. I've changed that spreadsheet dozens and dozens of times. So the point I'm getting at is whether it's the basic QC and FS data or any of the interpretations, the way I have my spreadsheet set up is I have one plot above the other, right? So I have the continuous plot, and then beneath it I show the individual data points. And I simply look at them together. And between the two of them, you really get some insight as to what's going on. It certainly doesn't have to be either or. Well, certainly it would seem we have some interesting stress history things going on at the case history site, especially within the Varved Clay. So it's a reasonable question to say, well, we've only looked at the seismic piezocone sounding. Was there some problem with that sounding? Maybe we're interpreting things that didn't exist. Well, I'm going to show you two things that I think will give us greater confidence in the interpretive results. To begin with, I performed an identical interpretation for the piezocone sounding, CPT01. And this plot superimposes the interpreted yield stresses. And again, I'm showing you each data point, the averaging, and the median values interpretation. The seismic piezocone, again, are the dark red circles. The piezocone soundings, I'm showing you for the first time, are the dark green circles. And keep in mind that the seismic piezocone goes down an additional 5 meters, so we could see down to the very bottom of the Varved Clay stratum. And I think you will agree that there's very good correlation between the seismic piezocone and the piezocone in terms of the interpreted yield stress. Especially that both cones, both soundings, show the significant scatter of interpreted yield stresses within the Varved Clay. I mean, there's just about near perfect agreement through the Pleistocene sand, for example. So I think it's reasonable to interpret that the interpretations of yield stress are not some anomaly from the actual sounding, but indicate that we have some very complex stress history issues with the Varved clay at the site. To give us even more confidence in the data, let's remember that we did 2 odometer tests. All right, so these are now traditional laboratory tests, so they have nothing to do with a cone penetrometer. How do the interpreted yield stresses from the odometer tests compare to the yield stresses from the cone penetrometer? Well, here's the one piece of data, and here's the other test. And keep in mind that the odometer tests were done prior to the cone penetrometer soundings, no less the cone penetrometer interpretations. And the consolidation test, the shallower one, actually indicated a higher yield stress than the lower one. Well, this was not unexpected, let's say, for the Varved clay. And by the way, you could see although I haven't highlighted them, you could see the 2 odometer tests on the average plot and the 2 odometer tests on the median plot. And I think the median plot is really the most insightful, and the average one is too, but the median plot is most insightful because it's hard to see, but this interpreted yield stress from the odometer test is right on 2 data points. So to me, and this of course is right on a whole bunch of data points down here. The point I'm getting at, I think the correlation between the yield stress interpreted from the odometer test and from the 2 cone penetrometer soundings is absolutely extraordinarily good, surprisingly good. And if I hadn't done the interpretations myself, I would have had a hard time to believe them. Well, there's several things we can draw, conclusions we can draw from this, several points I want to make from this. Number one, I think we have great confidence that these outliers of yield stress that we see here from the interpreted cone penetrometer soundings, they're not wrong. There's clear indications that during the depositional and post-depositional history of this 25 meters of Varved clay at this site, there are some very complex stress history behaviors. Now, whether it was intermediate desiccations or ice loading or reloading, I don't think we will ever know conclusively. But clearly, this Varved clay has a very complex stress history. And the fact that the odometer tests and the interpreted cone penetrometer soundings give us identical results give us confidence in this complex stress history. Another conclusion is that there's actually a warning here about the odometer data. Now, normally as we know, odometer tests are slow, they're expensive in practice, but we tend to think of them as the gold standard. We tend to think of them as this is the ultimate ground truth. Now, if this were a traditional project without the 2 cone soundings and all you had were these 2 pieces of data from the odometer test. Now, keep in mind, as I pointed out earlier, all the foundational alternatives that were investigated for this project placed the foundation somewhere up here in this sand stratum, meaning that the Varved clay was going to be stressed by the foundation alternative, whatever it turned out to be. Which means that you more than likely wanted to keep the stress increase on the Varved clay from the foundations below the yield stress, so that all the settlement that occurred under the stress implied by the building foundations would be in the recompression range. Now, if all you had were these two odometer tests, trust me, from having worked with Pleistocene fine-grained soils for my entire almost 50-year professional career, a very logical interpretation would have been that you had an exponential type of yield stress plot that was very high here at the top of the varved clay, decreased exponentially, and trended down towards normally consolidated with depth. We see this type of yield stress plot in other varved clay areas. We see it in non-varved clay Pleistocene clays. For example, look at any of the literature on the Boston blue clay. It appeared in countless publications over the decades. You see this desiccation crust is a very significant signature of Pleistocene fine-grained deposits, whether they're varved or not. But we don't have that here. We don't see this desiccation crust here. Yes, this is higher, but it does not appear to be related to a desiccation crust, because notice that the overall main trend of yield stress is fairly continuous from the Pleistocene sand all the way down through here, through this well-behaved zone. So this, in my opinion, would be a case that if all you had were the two odometer tests, you would be tempted to believe, okay, the yield stress is high up here, so I have quite a bit of stress to work with from the foundation. The reality is you probably have a much smaller stress to work with, and I'll show you some additional stress history plots to emphasize the point I'm making here. So, bottom line. The conclusions I draw from this slide is that the two cone penetrometer soundings at this site gave very consistent interpretive results with respect to yield stress, number one. Number two, very good correlation between the interpreted yield stresses from the cone soundings and the two odometer tests. I mean, it doesn't get any better than this, especially for a site that clearly has a very complex stress history. Number three, the varved clay at the site has a very, very complex stress history. I doubt we could ever reconstruct how it came to be. It just is. And it points out, again, something I mentioned earlier in this presentation. Varved clays are not some homogeneous material that's the same around the world. It's not even the same within the Hudson Valley Varved Clay. It's not even the same within Glacial Lake Hackensack. Trust me, I've done extensive work throughout the Glacial Lake Hackensack and other portions of the Glacial Lake Hackensack. You have this very distinctive crust that we tend to see in Pleistocene fine-grained soils. So if there's anything that shows you that sums up the benefit of doing cone penetrometer soundings, even on a small project, it's this one slide, in my opinion. We get estimates of stress state in coarse-grained soils that we cannot test routinely and reliably in the laboratory for stress state. And we get lots of data points for stress state in fine-grained soils that on a small project you might only have the budget to do one or two or very few odometer tests. Well, we can look at this stress state data in some other ways. Let's do that now. What I'd like to do now is look at stress history from a couple of other perspectives, beginning with overconsolidation stress difference. This is a parameter that we don't use as much as we should, I think. OCD is simply the yield stress minus the current vertical effect of overburden stress. And what we're looking for is depth-wise patterns of overburden stress. For example, if you were to see a uniform OCD versus depth, that would suggest that an entire area was unloaded a uniform amount at some time in the past, either by natural processes or human action or whatever. So these are the same three plots, all the data points averaged over plus minus 150 millimeters and the median over plus minus 150 millimeters. Again, for the averaging and median assessments are for the same reason of trying to reduce some of the scatter or noise, if you will, in the results. And the results are what they are. I mean, it's indicates that while there seems to be some perhaps nominally reasonable uniform overconsolidation stress difference in the Pleistocene sand cap, there does not seem to be distinct pattern in the Pleistocene Varved Clay, either the upper or the lower zone. And again, this is OCD comparing the piezocone CPT01 with the seismic piezocone, and again including the odometer data. I've just highlighted it in this plot, but you can see the odometer data points in the average and median plots as well. And again, as we found with yield stress, the two cone penetrometer soundings at the site, the piezocone and the seismic piezocone, agree very well. And there's also excellent agreement with the interpreted OCD based on the two odometer tests. The next is a more familiar term, the yield stress ratio, which is the currently preferred term, what for many, many decades we call the overconsolidation ratio, OCR. The term yield stress ratio is preferred now as you recognize that yield stress can be the result of many things. It's not just physical overconsolidation, as was historically at least implied, if not assumed in the past. There are many reasons that soils can exhibit a yield stress greater than the current vertical effect of overburden stress. And again, here's all the data points, the averaging plot and the median plot. And we do detect some trends with depth, but then again, when we get down into the Varved Clay, the pattern becomes more irregular. And again, I think we're looking at a couple of zones within the Varved Clay where something else happened in the past. Again, it may have been some intermediate desiccation or ice loading or something that is giving us these zones that seem to show abnormally high overconsolidation compared to the bulk of the strata. Again, just highlighting the definition of yield stress ratio simply being yield stress to the current vertical effect of overburden stress. And once again, comparing yield stress ratio for both cone penetrometer soundings at the site as well as for the two odometer tests that were performed. And again, we see similar patterns that what we've seen for some of the other data portrayals of overburden stress, of yield stress, overconsolidation stress difference, etc. That the two cone penetrometer soundings are in agreement, and the two odometer tests are also in consonance with the interpreted results from the penetrometer test. So again, with agreement between laboratory testing and the cone penetration test interpretations, this combined, I think, gives us much greater confidence in what we're seeing is indeed correct and not just some incorrect reading or some bad data points or something like that. And the final stress state parameter I want to look at is K sub O. Some people call it K0, K0. This coefficient of lateral earth pressure at rest. And we see again a pattern that suggests an overall pattern to the Pleistocene strata, the sand and the Varved clay, but some localized zones where clearly something has happened in the geologic past to create zones of higher yield stress and greater consolidation. We move on now to shear strength, which I've divided up into a discussion of coarse and fine-grained soils. We'll start off with talking about the coarse-grained soils. And we have the ability with empirical parameters, empirical correlations, to infer the peak triaxial phi angle and compression, the constant volume or critical state value, and the dilatancy value of phi, which is simply the arithmetic difference between the peak and constant volume critical state values. And again, because these correlations are based on IC and nowadays ICN, they will give us a result anytime I sub C or I sub Cn is less than 2.6, which is the assumed threshold between coarse and fine-grained soil behavior. So that's why we have data not only in the Pleistocene sand, as we would expect, but we have it within certainly the upper portion of the Varved clay that exhibited very sand-like characteristics in many places. But we see very believable values, very nice patterns, gives us confidence in the inferred results from the cone penetration tests. Moving on now to fine-grained soils. The empirical correlations for the cone penetration test allow us to evaluate both the drained phi angle, peak phi angle in triaxial compression, as well as the undrained strength using several assumptions or correlations based on direct simple shear, critical state soil mechanics, and the so-called cone factor, NKT. Cone factor has for many decades been a hallmark of the cone penetration test, where we seek to relate the Q sub C from the cone penetration test, the tip resistance, to the undrained shear strength using a parameter that's called N or N sub K or N sub KT. That is the so-called cone factor. The one thing I do want to point out is that, and this has been Dr. Main's research in the last few years with his graduate students and colleagues. As I said, the last few years, Main has focused on fine-grained soils. And one of the things he's found is that the correlations one has to use for the drain phi angle are really very dependent on the structure and sensitivity of the clay. So if you're looking to infer drain phi angles from cone penetrometer soundings, you want to be very careful in that there are different correlations depending on whether the clay material is lightly over-consolidated, heavily over-consolidated. If it's heavily over-consolidated, is it very structured and fractured? Dr. Main's research has found that one needs to use different correlations depending on the over-consolidation of the soil, the yield stress ratio, as well as this BQ normalization parameter that I mentioned briefly. early on is an important factor in assessing which empirical correlation you use. So the point I'm getting at is you do have to pay some particular care when you're dealing with empirical correlations for cone penetrometers and fine-grained soils. It's a lot fussier, that you have to pay a lot more attention to yield stress ratio and sensitivity. You see here both Dr. Main and Dr. Robertson have come up with correlations for sensitivity. So it's trickier when you're looking, the bottom line is that when you're looking to infer the shear strength of a fine-grained soil, whether it's the undrained strength or the drain strength, a lot fussier with the correlations. You have to pay a lot more attention to detail, be a lot more careful about what you're doing. That brings us to soil stiffness and structure assessments, which is shaping up to really be an area where the cone penetrometer, by virtue of the seismic piezocone, is now allowing us to explore things that heretofore we really have not been able to get into. So I would say in all of these other areas, stress state, shear strength, while certainly the cone penetrometer has allowed us to do some very interesting, useful things, to do things beyond that are incapable of ordinary laboratory testing, for example, with stress state of coarse-grained soils. If there's one area where the cone penetrometer has really allowed us to do things we could really never do before, it has to do with soil stiffness and structure assessments. And it's really, this is where the piezocone, as you'll see, is an absolutely essential tool. I can't stress that enough, that in any modern site characterization program, whether it's a large project or even a small project, where, as you see with this case history, they did two cone penetrometer soundings. One of them was a seismic piezocone. The seismic piezocone is really, it's no longer a luxury or an experimental tool or a research tool. It's an everyday must-have, must-use tool, in my opinion, in everyday geotechnical and foundation engineering practice. So let me first discuss what can we infer about soil stiffness and soil structure, microstructure, just using the QCFS-U2 data that you obtain from both the piezocone and seismic piezocone soundings. When we only have these basic data from a piezocone or seismic piezocone, we can make empirical assessments of soil stiffness, but they are very limited in terms of applicability. This is because these empirical correlations are all based on this young, well-behaved soil behavior, as I've defined earlier in this presentation. So that means soils that do not exhibit any significant aging, cementation, nor are they sensitive if we're talking about fine-grained soils. The more serious problem that I see is that if a soil does contain structure or microstructure, or if it's a particularly sensitive fine-grained soils, they cannot be identified by these empirical correlations. You know, it's not like I showed you previously. Dr. Main had 3 equations for yield stress in a fine-grained soil, and if the 3 gave the same results, more or less, well, then we can infer it was a nice, normal, well-behaved clay. If the 3 gave divergent results, then we could assume that it was something out of the mainstream. Unfortunately, with, at least at this point, with soil structure and sensitivity, there is no metric just using the QCFS-U2 data. There's no way to say, oh, look at these data, they tell me that the soil has structure, the soil is sensitive, and I shouldn't use these correlations. So that to me is a bigger problem. we have correlations, and they work very nicely. In fact, you'll see that they work extraordinarily well for nice, normal, well-behaved soils, but they don't tell us when the soil is not nice and normal. And I'm going to show you actually two examples just to make the point very clear. I'll show you, of course, the case history, but also show you some data from Kennedy Airport to really make clear what I'm talking about here. So I said it before, but as I said, I really don't think I could say it too often that performing a seismic piezocone sounding and generating site-specific shear wave data really an absolute necessity if you want to get a proper handle on site-specific stiffness in the presence or absence of soil structure, microstructure, or sensitivity. And as I said, I'm going to illustrate this to make the point. Well, let me first show you the empirical correlations just based on the QCFSU2 data. This would be the inferred profile of Gmax or G0 if you prefer, the small strain elastic, linear elastic shear modulus. This would be the forecast pattern versus depth. This would be the reduced rigidity index for coarse grain soils only. And again, this is the most correct for the Pleistocene sand stratum. We do get data or forecast down here simply because the I sub C was less than 2.6 for some of these data points. And this is the rigidity index for fine grained soils, and you see that there are two ways of doing this. One is based on critical state soil mechanics. So they give us in this case, two very different profiles of the rigidity index for the fine grained soils, which is predominantly here in the Varved stratum, of course. Well, let's move on to the more substantial discussion, and that is soil stiffness and structure assessments based on shear wave data from a seismic piezocone sounding. To illustrate what I've been saying now several times, why I feel that a seismic piezocone is essential on every project where cone penetrometer soundings are performed, let me back that up by first starting with the case history that we've been discussing in this presentation, and then I'll show you some additional information from Kennedy Airport. So these are the basic results for the case history site in the Connecticut Valley Varved Clay. This first plot is shear wave velocity, and the small green data points are the empirical results I've shown you previously, and the red squares are the actual measured values. You note that the shear wave velocity measurements were not performed below 30 meters. There's certainly no reason why this could not have been done. The decision was made by others on this project to terminate them at that depth. But certainly you see this is really excellent agreement. I mean, I've been able to compare empirical and measured values of shear wave velocity for many seismic piezocones at several different sites now. And this is really excellent agreement. Although we notice down here, we start to see some deviation. And although it's conjecture, it's quite possible that this deviation may have continued for the lower part of the Varved clay stratum. This is a normalized value of shear wave velocity. And again, the reason we normalize is to remove the effects of confining stress from the picture so that we can see true changes. And we see when we do normalization that certainly the Pleistocene sand stratum and much of the upper Varved clay stratum basically had the same normalized shear wave velocity And that continues down here with the measured values. And finally, we have the small strain shear modulus, Gmax, or G0 if you prefer. And again, we see the empirical values, the green dots, and the measured values. By the way, you'll notice here with the measured values for these two plots, I did this based on the mean and median values of the soil density to calculate shear wave velocity, to calculate small strain shear modulus from shear wave velocity. Using the theoretical equation, you need to have the soil density. So what I did was to, rather than just use the density, since these shear wave velocity measurements were made every meter, rather than just use the estimated soil density at the depth of the shear wave velocity, I averaged it for halfway up, halfway down from the point of the shear wave velocity. And as you can see, whether I used a mean or arithmetic average, if you will, or median value, really made no difference. So the conclusion we would draw here is that at this particular location, for the most part, there's agreement between the empirical and the measured values of shear wave velocity and the calculated values of Gmax. I'll show you an example in a minute where that is certainly not always the case. If we look at rigidity factors, these are the rigidity factors. There are different symbols for the coarse grained soil and fine grained soil. This is reduced rigidity factor for coarse grained soil, rigidity factor for fine grained soil based on the calculated Gmax data. And over here are the empirical values that I've shown you previously, shown all on one slide, both coarse and fine grained soils together. And you see that there's reasonable agreement. I mean, rigidity factors are always notoriously difficult to estimate. So I would say that overall there is, since these two are drawn to the same scale, you can see that there is reasonable agreement between the measured, if you will, and the empirical values. Well, as I've been saying, soil structure is assessed using several empirical parameters that have been defined specifically for this purpose. The current state of practice is the empirical parameters are crafted around a parameter called a small strain rigidity index, I sub g, that is arbitrarily defined. It's based on the measured value of the small strain shear modulus, Gmax or G0, as calculated from the measured values of shear wave velocity from a seismic piezocone sounding. Now these small strain rigidity index are used to assess soil structure, and they're typically the way you see the plots. And here's a typical plot from Dr. Robertson's work, shows the normalized tip resistance. Here's the small strain rigidity index down here, and you see it's the basically stiffness to strength, if you will, is the definition of rigidity index. And typically what you see are upper and lower bounds of what are called modulus number, capital K sub G. And here's this particular definition of modulus number. Now I'll just tell you now, and I'm going to be illustrating this in greater detail, a couple things about modulus numbers. First of all, there are multiple definitions. These have evolved over the last few years, and people keep changing the definition a bit. Second, the notation is not always consistent. In this particular plot is called K sub G star. Sometimes the star is left out, so it can get a bit confusing. You really need to look at how exactly modulus number is defined in a particular plot that you're looking at, because these boundaries, so what you're seeing here with these two slope lines, 330 and 100, anything that falls within this bound would be considered an ideal or normal soil. Right? Young, well-behaved, unstructured, insensitive, etc., etc., etc. And anything that deviates, the deviation is going to tend to be in this direction. The greater the deviation in this direction, the greater the indication of structure or microstructure, if you will, to the soil. I've added this to just show you that some of these plots will also indicate that if you go in this direction, this is an indication of increasing compressibility. So this is currently the most advanced definition of modulus number. I'm going to show you some older definitions in a minute. So this is the same plot, but for our case history site. And you see that the values that I showed you on the previous slides, they're pretty well clustered along or within the boundaries of normal soils, well-behaved, etc. Slight deviation going towards aging. So there's a slight indication of aging at a couple locations. And we saw that primarily down towards the lower part of the Varved Clay stratum, where the measured values were deviating from the calculated values, the empirical values, suggesting that that very bottom part of the Varved Clay may have a little bit of structure to it. This is another way to portray the data on a depth-wise basis. Now here I'm showing you three different definitions. And I've arbitrarily called them KG1, KG2, KG3. This 1, 2, 3, this is my notation. You see very slight definitions. They all involve the small strain shear modulus and the tip resistance to some extent. They involved different normalized values, which tends to set these different equations apart. All right, so here's Q sub T, the corrected tip resistance. Here's Q sub N, the normalized corrected tip resistance. So, as I said, the notation you'll see for this modulus number is not always consistent. You need to focus on what equation. And if you're looking at a paper or some other reference document, whoever prepared that paper or document, they should define what they consider to be modulus number. And you see that the boundaries of KG do vary depending on how modulus number is defined. Here's the most advanced one that I used for the case history site we're looking at. And here you can see how things fall with depth. And you see a little bit of deviation from indicating perhaps some slight structure at a couple points, but nothing really major at this particular location at least. So this just highlights what I've been saying, that the terminology and notation for modulus number are inconsistent in publications, sometimes even by the same author. So you really need to look on a publication by publication basis what the notation is, how it's defined, etc. And finally, there are a couple of liquefaction related parameters. I'll just point these out just for information. Although seismic liquefaction was not an issue at this project site. This is a parameter capital Y that you see in some publications. And ASF is age scaling factor. This is kind of interesting because here the boundaries are not modulus number, but they're inferred age. So you see this is the Holocene, this is Pleistocene, this is Tertiary. And this is kind of interesting because what this is implying is that the sand cap and the upper 10 meters of the Varved Clay are indeed Pleistocene type ages, as we know. But what's interesting is that this suggests that as we get into the lower portion of the Varved Clay that we're starting to see material that possibly is older. I'm not saying it goes back to the tertiary, but it may be from some older portion of the Pleistocene. So this is the sort of thing that I think geologists, for example, might have a particular interest in. That, again, we tend to think of, or at least we used to in the past, think of, well, okay, here's this Varved Clay stratum. It was all placed in the same glacial lake at more or less the same time frame. Well, that's not necessarily the case. We now know that there have been many advances and retreats of the ice margin, and these glacial lakes may have been added to at many different times during the Pleistocene. And so it's not surprising that perhaps some part of that Pleistocene Varved Clay here is older than the upper material. Now, the difference between the empirical results based on assumed young, well-behaved soil behavior and the actual measured results based on shear wave data from a seismic piezocone sounding were really quite modest at the case history site we've been looking at. But this is not true elsewhere. And I want to use another case history to illustrate that. We don't have to look very far. We just can stay within the New York City metropolitan area and look at the site of Kennedy Airport that is about 40 kilometers away, for an example. Now, the John F. Kennedy International Airport site was affected by the same sequence of Pleistocene glaciers that affected the Hudson Valley Varved Clay case history site we've been looking at, albeit in a very different manner. There is no Varved Clay under the Kennedy Airport site, but the point is both sites were subjected to the same basic geological events. So it's of interest to discuss the recent use of the seismic piezocone at Kennedy Airport over the last decade or so, as this provides some convincing, what I call ground truth, as to just how essential actually recording shear wave velocities using a seismic piezocone is for identifying and assessing soil structure. Now, as I indicated at the beginning of this presentation, in 2020 I posted on YouTube, the first posting on my YouTube channel was a presentation about the geo-history of Kennedy Airport. And what's interesting is it's a very large site. It's about 2,000 hectares, 5,000 acres, current airport property, but the subsurface conditions are really surprisingly uniform in the scheme of things. And this is especially true within the so-called central terminal area, where most of the reconstruction has taken place in the last few decades. So whether it's basic QC, FS, U2 data from a piezocone or seismic piezocone sounding, or N160 values interpreted from standard penetration tests, these data tend to be very, very similar and repeatable, especially throughout the central terminal area, the CTA of Kennedy Airport. And this is a very typical subsurface profile. I've used it in my earlier presentation on Kennedy Airport. You have Holocene sand fill. This was placed by dredging from nearby Jamaica Bay. So this is predominantly a medium fine to fine sand that was placed hydraulically. This is underlain by the natural organics, primarily organic clay with some peat. And this is just the tidal marsh deposits of Jamaica Bay that were again created when we had sea level rise and typical drowning process that creates tidal marshes. And finally, we have a rather substantial thickness of Pleistocene outwash sand. As you see, it's typically 30 or more meters thick. And for those of you who are not familiar with Kennedy Airport, bedrock is quite deep. Bedrock is 250, 300 meters below the ground surface. So there's many other sequences of soils under here. I discussed them in detail in my presentation on Kennedy Airport if you are interested. Well, for many years, the Pleistocene outwash sand stratum at Kennedy was considered a single geologic formation called the Upper Glacial Aquifer, the UGA. In recent years, geologists have rethought things and now identified that the UGA is really three separate formations. One of them including an older organic clay from an earlier stage of sea level rise. Now this older organic clay, the Wantagh Formation, is largely absent throughout Kennedy Airport. I suspect it's probably been missed a lot. I mean, the vast majority of subsurface exploration at Kennedy has been traditional borings, standard split spoons taken every 1.5 meters, every 5 feet. So it's you could easily miss a 6-inch or 1 foot layer. You know, if you have a few tens of millimeters thick layer of this old organic clay, it's very easy to miss that in sampling. But I think it's a fair statement to say that this is largely absent throughout the Kennedy Airport site. The same is not true in some surrounding areas, and again, I discussed this in some detail in my presentation on Kennedy Airport if you'd like to learn more about this. But for our discussion purposes, I spent many portions of my professional career over the last almost 50 years working at Kennedy Airport on different projects. I've looked at countless numbers of borings and more recently cone penetrometer soundings of all types. And I think for discussion purposes, we can think of this upper glacial aquifer as really having a dividing line at about a 20-meter depth is convenient for discussion purposes. Below this 20-meter depth, and this, by the way, as you can see, it really fits very neatly into this separate Belmore-Merrick Formation understanding of the upper glacial aquifer that we have now. The deeper parts down here tend to be denser. They tend to be coarser grained. So there's a very definite transition at roughly about the 20-meter depth. And I'm emphasizing this because for some of the things I'll show you subsequently. Well, the thing I want to focus on here is that they've been using the seismic piezocone at Kennedy Airport for the last decade or more. And it's revealed some very interesting and quite unexpected results that indicate subsurface conditions, at least stiffness-wise and structure-wise, within the central terminal area, are perhaps not quite as uniform as we've always thought historically. And I'm going to illustrate this using two seismic piezocones from within the past decade. I'll call them sCPTa and B. Now, they were performed for the same project during the same time frame, but they're a couple hundred meters apart. For confidentiality reasons, I'm not going to mention where this was in the central terminal area, but it was a single project. But as I said, different portions of the project area. Now, although I'm focusing on these two soundings, they weren't unique, they weren't outliers. What I found, and I was not involved in the particular project where these were taken, but I was provided with the information several years later for research purposes. And I found that I looked at, I forget how many seismic piezocones were performed. It was probably in the maybe 10, 12, something like that, perhaps even more. But they all tended to group either they were similar to A or they were similar to B, and that's the point I'm getting at. And furthermore, all the seismic piezocone soundings that were similar to sCPTA were clustered in that same one area, and all the seismic piezocone soundings that were similar to sCPTB were clustered around that area. So in my mind, it was pretty clear that we had two very distinct areas, and we had several very similar seismic piezocone soundings in each of these two areas, A and B as I'll call them. As I said, I was not involved in the project in which these soundings were made, but the raw data were made available to me afterwards for research purposes. So all the interpretations I'll show you are my own. They're not showing you work or interpretations done by somebody else. Okay, first let's look at the basic results. Here's the shear wave velocities for location A, and the continuous green curve is the calculated based on empirical equations. And again, these empirical equations, the same equations I used for the Hudson Valley Varved Clay site I showed you a little bit earlier. These assumed normal, young, well-behaved, typical soil behavior. And you see the measured values shown by the red dots. And the correlation is excellent. I mean, it doesn't, believe me, it doesn't get any better than this in terms of correlation between measurements and empirical values. So very clearly, this site A is a normal soil site. Well, if we look at site B, well, quite a bit different. Look at again, the green curve is the empirical value based on young, well-behaved soil behavior. You can see the deviation with depth kind of begins below 15 meters, but certainly pronounced at around 20 meters and below. This is a very significant deviation here. And it's not just one data point, it's very consistent. All right, so if we compare these two, we see that clearly at about below the 20-meter level, we have very, very different stiffness behavior. Well, we next look at the small strain shear modulus, G max, G naught if you prefer, for the A site. And again, we see excellent correlation between what we would get from empirical correlations versus measured values. And again, for the site B, we see significant deviation as we get down to maybe about 18 meters or so, certainly below the 20-meter depth. We see significant deviation indicating some structure. And again, that 20-meter depth I found at Kennedy Airport is kind of a nice round number, magic depth, if you will, for a real noticeable transition in the composition and the behavior of the upper glacial aquifer, which, by the way, I should have mentioned, that is the bearing stratum. Everything at Kennedy Airport, even not only buildings and roadway overpasses, things like that, but even some of the very tall light poles, they're all supported on deep foundations. Driven piles, primarily tapered piles. Timber piles were used in the past. In more recent decades, it's been monotube piles. And now that monotube's out of business, it's been taper tube piles. But this upper glacial aquifer has always been the bearing stratum for pretty much everything at Kennedy Airport. Well, let's move on with our assessment, looking at the stiffness parameters based on small strain rigidity index and modulus number that I defined previously and illustrated for the Hudson Valley Varved Clay site. So here's the results for sCPTA, our well-behaved site. and you see everything falls pretty much within the bounds of well-behaved or normal soils. I do want to deviate for a second and point out to you that, as I noted earlier, the definition of modulus number has varied over the years. This is the latest version, and that's the version I use for the Hudson Valley Varved Clays that I discussed previously. The assessments I'm showing you now for Kennedy Airport I actually did several years ago. So at that time, this was the definition that was in vogue, and this was the definition I used. So a little bit older definition. The difference is really in the term here. You see that this is based on the corrected tip resistance, Q sub T. This is based on the normalized tip resistance, lowercase q sub n. Otherwise, the parameters are the same. You see G naught, G naught, G max, if you will, and QTN, QTN. So I just wanted to make that clear. That's a little bit different definition, and as a result, the kg boundaries for what constitutes normal soil are slightly different as well in terms of the numerical values. So here's the sCPTb site where we saw some deviation in shear wave velocity and small strain shear modulus, and indeed we see some deviation into the realm of what we would consider to be some sort of structure or microstructure. Right? You could compare the two more readily here. I've highlighted to show the difference. Well, we can look at this another way by looking at modulus number as a function of depth. And here we see the A site, the well-behaved site, falling pretty much within the bounds of normal behavior. And if we look at the B site, we see certainly, again, notice that the magic kind of, you get down below about 19 meters or so, that magic 20-meter depth, we start to see some deviation. So this deviation we see here, we translate over to this plot, we see that same deviation. This deviation we're seeing here, this pinpoints where that deviation is occurring. And as we see, that deviation is primarily below that magic 20-meter depth, if you will. So this is suggesting that certainly in the deeper portions of the upper glacial aquifer stratum at Kennedy Airport, that we might have some structure, some microstructure, at least in places. It's here, but it's not here. And this was to me the very unexpected result when I looked at all these results, given the fact that these two seismic piezocones reflect conditions within the same project. Right? So within the same general project area, no more than a couple hundred meters apart, we have, in one part of the site, we have several seismic piezocones that look very similar to this, and another part of the site, we have several seismic piezocones that look like this. And as I said, I've worked at Kennedy Airport since June of 1972, when I first started my professional career. And this was really, to me, quite amazing. I mean, that you don't see the difference in if you were to, I haven't shown you this, but if I were to show you from soil borings, if I were to show you the QCFSU2 data from these two seismic piezocones, they would essentially be identical. But when we look at, so we would not just base the, I mean, if we were to look at the other cone results, the QCFSU2, we would not see any meaningful difference between these two soundings. The difference only shows up with the measured shear wave velocity. Had we not done seismic piezocones, we would not have detected this anomalous behavior between these two soundings. And that's the point I want to make here. This is the key thing I want to make, is that if we compared SPTN values, you would not see a difference. If you compared the basic QC FSU2 data, you would not see a difference. The difference only shows up with the measured shear wave velocity. You can only get the measured shear wave velocity from a seismic piezocone, and that's really the lesson I want to present to you here, or have you get from looking at this case history. So the conclusion that I draw from this recent experience at Kennedy Airport is that the seismic piezocone sounding should always comprise some portion of every project on which the cone penetrometer is used, no matter how small the project. We saw on the Hudson Valley Varved Clay site, you have 2 cones. One of them is a seismic piezocone. And it's for the simple reason that unless site-specific shear wave data are obtained from the seismic piezocone, there's no other way to reliably detect soils that contain some structure or exhibit some atypical stiffness behavior. If you have large projects where you might perform the site characterization in phases, in my opinion, it would generally be desirable to perform at least some of the planned seismic piezocones in the first phase, because this will give you a heads up, an advance warning of any site-specific soil structure as early in the program as possible. As I said, this difference at Kennedy Airport was totally unexpected. This is not something, I've worked at Kennedy for almost 50 years. This is not something that I would have expected to see. I can't explain it, and I've talked to people, including some who are far more expert with cone penetrometers than I am, have looked at seismic piezocone data from around the world, literally, and they were perplexed as to understand what this could be, and given the fact that it was quite repeatable. As I said, it wasn't just one seismic piezocone had oddball readings. There were several seismic piezocones in the same area that had essentially very similar, if not identical, results. And as I've been saying, the presence of soil structure is not known or even suspected beforehand. And as we could see, it could even vary within the same site. So I think this, the reason I use this case history from Kennedy Airport was to show you that you can have unexpected results even on the same project a couple hundred meters apart that exhibit different stiffness behaviors and evidence of soil structure. Well, let me wrap up this presentation with some closing comments. And I want to make some comments in 3 topical areas, beginning with the Hudson Valley Varved Clay. Well, published work with respect to the Hudson Valley Varved Clay is what I call a mixed bag. The vast majority of publications that I've found in the public domain have been by geologists. I feel that our geology friends have been very generous in sharing their interpretations and reinterpretations of the very complex geological history of the Hudson Valley Varved Clay, especially in the New York City metropolitan area, where the combination of multiple Pleistocene terminal moraines combined with numerous advances, retreats of the glacial margin within a glacial episode have resulted in a very complex scenario of multiple overlapping glacial lakes and a very complex stress history. You have combinations of desiccation, ice loading, and hopefully I've illustrated to you that at least at that one site I showed you in the Hudson Valley, in the glacial lake Hackensack, that the stress history is clearly very, very, very complex. It does not fit the nice, neat picture of desiccated crust grading down to near normal consolidation that you find in many other fine-grained glacial deposits, Varved clay or otherwise. Now, what I call east of Hudson areas centered around New York City itself have benefited from several large projects in recent years, both on land and in the water. And most of these projects have included the cone penetrometer as an integral part of their site characterization program. So these large projects have generated substantial amounts of subsurface data, and geologists have used this information to very good effect to revise old interpretations, advance new interpretations. Although I don't see that in reading these papers, and as you can see here, we really have Cheryl Moss, who is a professional geologist with a geotechnical consulting firm in New York City. We have her to thank for a very extensive publication record over the last 15 years or so. And this is the result of large projects that were worked on by her firm. And as I said, geologists have been very generous in terms of taking this huge volume of new data and writing some very nice papers. You can find all of these. These are all in the public domain. You can find all of these online with a little bit of searching. But I've read all these papers, some of them more than once, and I don't see that either the piezocone or seismic piezocone data have been used to estimate stress state. Where there is use of geotechnical data, it's primarily SPTN values, and yeah, that provides some gross idea of, gee, this is loose, this is dense, but it really does not give you any idea of stress history. Anything dealing with stress history in these papers tends to rely on odometer data, but I think we could do a lot more if we reviewed the CPT data for stress history. Well, while geologists have been very generous of sharing their knowledge, I really can't say the same of geotechnical and foundation engineers. And my personal opinion, and I emphasize it is my opinion, is that from what I've seen, and I certainly know of these large projects that have been performed in the New York City area, I know a lot of the people who've been involved in these projects. I personally have not been involved in these projects, so I can say this as an interested outside party, that increasingly on these large projects where a lot of these data are generated, they tend to be design build in nature. These tend to be public projects. A lot of public agencies have gone to the design build concept. They perceive that to be better for their interest than the traditional design bid build model that had been used for a very long time in the New York City area. But on these large design build teams, they're all controlled by large multinational construction firms. And I'll just, I will reserve any further personal opinion, but it does not appear that they perceive it to be in their interest to share what knowledge they have obtained in terms of disseminating it in a public forum, saying, gee, we just did this large project, and here's a bunch of interpretation of what shear modulus is, or shear strength is, or phi angle is, or anything like that. Which in the past this was true. I mean, when in the old design bid build, very often the design engineer would get the approval of their client, who was the project owner, to at some point later on to present some engineering interpretation of the data. So the reason I'm pointing this out is simply to make everyone aware that if you look for geotechnical and foundation engineering knowledge with respect to the Hudson Valley Varved Clay, It's really publications from decades ago. It's probably the same publications I read as a student and entry-level engineer in the 1960s and 1970s, where people wrote papers and they showed you the results of odometer tests and perhaps some SPTN values, things like that. So unfortunately, the geotechnical knowledge with respect to the Hudson Valley Varved Clay is quite ancient. And as we know, it's because it is very site specific. I think it's very dangerous to try to extrapolate knowledge about the Varved clay from one site to another without some care. So, as I said, what you will find in the public literature tends to be very traditional site characterization results. Bottom line is that it's clear, in my opinion, that both geologists as well as geotechnical and foundation engineers would benefit by sharing knowledge with respect to the Hudson Valley Varved Clay. You know, understanding that conditions do vary from site to site, but at least sharing data saying, look, at this site, this is what I found. And at least we would have some idea of the extent of the variation of subsurface conditions within different portions of the Hudson Valley Varved Clay in a geotechnical sense. We move our knowledge into the 21st century, if you will. So hopefully in some small way, the case history that I discussed in Glacial Lake Hackensack provides some insight into really the tremendous volume of interpreted outcomes you could get from piezocone and especially seismic piezocone data, and how we could use those outcomes at any site that is underlain by the Hudson Valley Varved Clay to improve our understanding of the soil properties of that stratum. And again, our geology friends would benefit from the stress data information as well, I would think. Would help them with their interpretations and reinterpretations of Pleistocene geology in the New York City area. I've hopefully showed you that Varved clays in general, wherever they are throughout the world, should not be generalized in terms of their behavior. They're very site-specific. They're going to be site-specific in the actual gradation of the Varved material, depending on the depositional history. They're going to be very site-specific in terms of the stress history in particular. Especially in areas where there may have been advances in retreats. The glacial lakes may have been deposited at different times. There may have been some intermediate ice loading, some intermediate desiccation, a lot of things going on that we can't possibly know or reconstruct at this point in time, but at least we can infer from the stress state history that we estimate based on CPT soundings. And again, given the wealth of information that's been made available for the Connecticut Valley Varved Clays, which, you know, I wanted to point out that the Hudson Valley Varved Clays are not just the same as the Connecticut Valley Varved Clays, but in a different geographical location. Not all Varved Clays are created equal. I next like to give you some personal insights or thoughts about what I perceive to be trends with respect to the cone penetration test. I've been in active continuous use of cone penetrometer data for both research and practice since the late 1980s. And although I'm not portraying myself as an expert on the cone penetrometer, I certainly have been using the cone penetrometer for more than 3 decades now. So in that time, I've developed some insights as to, as they say, an interested outsider, if you will, as to what I see some of the interesting trends that have been occurring over time. I think first and foremost is there's the overall broad movement to using soil properties parameter that are normalized to overburden stress. That's perhaps the biggest trend I've seen in recent years. Is we don't just use the corrected tip resistance, we use a normalized tip resistance. And I think you've seen that in a number of the slides I've shown. And if you look at some of these empirical correlations in detail, you'll see that capital QTN parameter, the normalized tip resistance, appearing again and again in empirical equations for soil properties and parameters. And normalization makes sense because it removes the effect of confining stress, overburden stress, and kind of levels the field in that sense, so that we can see trends or changes in soil behavior characteristics. And this is nothing new. I mean, if you think about it, we started doing this with SPTN values decades ago. In the big awakening, as I call it, for the standard penetration test of the 1980s, when people began to realize just how non-standard the standard penetration test was. That's when we started doing things like, instead of using field end values, we used N1 values, normalized to like 1 metric ton per square foot, for example, overburden stress, things like that. And that normalization was separate from the correction for energy. Okay, so N1 is different than N160, where you corrected for the 60% efficiency. So because the normalization of cone data has impacted just about every aspect of interpreting cone data, to me it's the single biggest change in the cone penetrometer in the almost 90 years that it's been used in both practice and research. Next importance to me is how we infer the soil that we're going through when we perform a cone penetration test. Obviously, we don't recover samples with traditional boring, so we've always had to infer the material we're going through. And in that respect, the fact that we now emphasize soil behavior type, more specifically normalized soil behavior type, as opposed to soil identification based on soil particle size and plasticity, as has been traditional in geotechnical engineering since the beginning of modern soil mechanics in the 1920s, this movement towards soil behavior type and a mechanical performance-based aspect to soil, to me, is quite significant. Now, as part of this movement towards inferring soil behavior as opposed to soil type or soil identification per se, the modified normalized soil behavior type index, ICN, and its predecessor, IC, have really emerged as essential parameters, not only in their own right. I mean, for example, we infer that if IC or ICN is less than 2.6, that we have a predominantly coarse-grained soil, for example. In addition to using that parameter directly, when you start looking at these other empirical parameters for all source stress state, et cetera, you find that this parameter turns up time and time again. So IC and now ICN have been used in many empirical correlations for other soil properties and other soil parameters. Really quite an essential property, or parameter, I should say. And as part of this movement towards soil behavior type is the increased focus on inferred dilative versus contractive soil behavior. And while this probably has the greatest relevance to the static and dynamic seismic behavior of soil, its greatest use is for evaluating coarse-grained soils with respect to seismic liquefaction. As I'm sure you know, certainly the early correlations for liquefaction of coarse-grained soils were all based on SPTN values. And in recent decades, we've increasingly been moving towards using the cone penetrometer data as well as shear wave velocities. And that's the nice thing, of course, about, again, to tout the seismic piezocone that obviously I'm a great fan of is to note that there are many correlations for seismic liquefaction that are based on shear wave velocity. So if you perform a seismic piezocone, you could basically do two separate assessments of liquefaction potential, one based on the Q sub C that you're measuring, one based on the shear wave velocities that you're measuring. Now, as part of this focus on dilative versus contractive behavior, this critical state soil mechanics so-called state parameter psi has emerged as really the parameter that is much preferred to relative density as the metric for assessing the consistency of coarse-grained soil. Much better, much more theoretical basis for using this state parameter as opposed to relative density. And I emphasize this because there are many parts of the world, and I say from firsthand knowledge here in the United States, where both academicians and practitioners tend to be what I call critical state soil mechanic phobic. We don't teach it, we don't use it to nearly the extent that we should, and certainly the state parameter is an example of this. Next, I would consider the ability to estimate stress state, the yield stress, the K sub O, for all types of soil, okay? All types of soil is to me one of the most significant developments of using the cone penetrometer, because as you know, with traditional soil sampling and laboratory testing, historically the best we could ever do with stress state was to estimate the yield stress for fine-grained soils. And as we know from thin wall tube sampling, we have disturbance issues. They exist all the time. It's not a question of, gee, do we have disturbance or not? It's a question of how much disturbance do we have. That's why I always put undisturbed in quotes, because it's to a certain extent, undisturbed is wishful thinking. It's a goal that we can never achieve with normal thin wall tube sampling. And I emphasize that because we know from decades of experience that disturbance of thin wall tube sampling will affect our estimate of the yield stress. One of the things hopefully you've gotten from the case history I presented today is that the relatively few, in this case only 2 odometer tests that would typically be performed in a relatively small project can actually be misleading in the insight and stress state, especially in sites such as the one I talked about in this presentation that have a very, very complex stress history. As I showed you, the 2 odometer tests, the shallower one actually had a higher yield stress. And if that's all you had, if all you had were those 2 odometer tests and the yield stresses from those 2 odometer tests, it would be, and I put myself at the top of the list, I would think it was, okay, this is just your typical Pleistocene fine-grained deposit. You've got a crust with a high yield stress, and then it decreases exponentially with depth to a yield stress that is close to being normally consolidated. That would be a very, very reasonable interpretation of those 2 data points. Well, in fact, it does not appear that the site, the Varved clay, had a crust on it. And it's not that the higher yield stress of the shallower odometer test was wrong. As I showed you, there were several data points from the cone penetrometer interpretation that agreed with it. But it was an outlier. It was a localized zone of whether it was desiccation or some other phenomenon that happened in the geological past. I don't know. We don't know. We'll never know. But it's an outlier. It was not representative of the stress state of the material. Now, in this case, relying on just the odometer test could have gotten you into trouble, because you could have overestimated the degree of overconsolidation. And again, it's important because for this particular site, the foundation loads were going to be transferred to that Pleistocene sand cap on top of the varved clay. So there was going to be stress increases to the varved clay from the foundation loads of the new structure. So the last thing you want to do is to overestimate yield stress, because you would underestimate settlement and you could get yourself into trouble. So I think that this turned out to be a very interesting case history from the perspective of showing you how, if all you had was a 2 odometer test, you could have gotten yourself into some trouble in terms of performance of the actual structure. Clearly, the combination of the interpreted data from the cone penetrometer soundings and the odometer data provided much greater insight and much higher degree of reliability on the interpreted outcomes. Now, the next milestone to me is the evolution of the seismic piezocone from a research tool to an everyday tool in routine practice on projects both large and small. And this has been very helpful because it allows us to measure site-specific values of shear wave velocity. And we're obtaining the usual QCFSU2 data at the same time. And we can estimate the site-specific soil stiffness with a much greater degree of reliability without having to resort to empirical correlations that are very restrictive in their assumptions and implications in terms of quote-unquote normal, well-behaved soil behavior. And the ability to measure shear wave velocity and actually measure the small strain shear modulus has increased our understanding of soil stiffness. And soil rigidity, which is the ratio of stiffness to strength, is not necessarily due solely to confining stress. It is also due to soil structure, which involves several behavioral factors of aging, cementation, and other factors related to the overall environment of the soil. And if I tie this into some of the research I've done with tapered piles, one of the things that Fellinius has noted with respect to the setup of driven piles in general and tapered piles in particular in coarse grained soil is that this setup or increase in axial compressive load bearing capability, it's not a strength increase, it's a stiffness increase. I don't think a lot of people appreciate that. Nowadays everybody understands, even design engineers, contractor, everybody understands that even piles, driven piles in coarse grained soil will tend to increase in their axial compressive load bearing as a function of time after driving. Call it setup, call it soil freeze, call it whatever you will. But I think there's a perception that somehow the soil gets stronger. It's not a strength increase. It has nothing to do with strength. It has nothing to do with pore pressure dissipation or anything like that. It is strictly a stiffness increase. So related to all this understanding of soil stiffness is the understanding that the behavioral age of a soil. By behavioral age, I mean, does the soil behave as if it is a young, recently placed soil, or is it show some effects of aging? The behavioral age of a soil is not necessarily the same as its geological age. All soil deposits only have one geological age. It's when was this soil deposited by nature, or when did humans place the soil at some point in the Holocene. Now, the behavior of the soil is not necessarily the same. Certainly, we can have soils that were deposited a long time ago, yet they behave as if they were a much younger, more recent soil. Why? Well, it's because the behavioral age can be reset. It can be reset by natural or human-induced mechanisms. For example, if you have seismic liquefaction, that resets the age of a coarse-grained soil. It's now going to behave, after the liquefaction event subsides, that soil is going to behave as if it was just placed yesterday, not as if it was placed perhaps back in the Pleistocene or older. More specifically, with respect to structure of soil or the combined effects of structure and sensitivity on the behavior of all types of soil, especially fine-grained soil. As I've noted, Dr. Main's research in recent years with his graduate students and other colleagues have really focused on fine-grained soil. And collectively, this has given us a recognition that, and again, this ties into the behavioral age issue I was just talking about, that the empirical correlations that we develop for the piezocone and seismic piezocone are based largely on mainstream or normal soils, if you will. And you see people use terms like young, well-behaved, unstructured, and sensitive, hourglass sand, vanilla clays, etc., etc. And that makes sense because the vast majority of soils that we encounter will fall into this normal or mainstream category. But we've also come to appreciate that there are soils that, either due to structure or sensitivity or both, are not in the mainstream behaviorally. And this is especially true of fine-grained soils. And I made this point earlier, but it bears some repetition. When you're working with the cone in cone penetrometer and fine-grained soils, you've got to be very careful about the empirical correlations that you use. And again, this is look at the work by Dr. Main in recent years. He's very detailed about this, that the first demarcation has to do with the yield stress ratio, the overconsolidation ratio, if you will. You know, if we have a relatively low yield stress ratio tending towards normally consolidated, what we call lightly overconsolidated, that behavior is going to be different from something that is more heavily overconsolidated. And if it's more heavily overconsolidated, does it have some structure? Does it have desiccation cracks in it, things like that? So this is where we start to look at things such as yield stress ratios. This B sub Q normalization parameter comes into play quite a bit. So people have been developing empirical correlations, but you have to use the correct empirical correlation that fits the particular soil that you're dealing with. So as I said, it's people have been developing, and I'm sure will continue to develop, a variety of metrics for evaluating whether soils are in the mainstream or not in their behavior. But I am emphasizing this because you do have to use empirical. The empirical correlations we have for the cone penetrometer are wonderful, but you never lose sight of the fact that they are empirical, which means that they were developed based on a certain database. And if you stray from that database, you can get in trouble. So you have to make sure that you're using these empirical equations correctly. You're using it for the material you have is in the database that is appropriate for that correlation. So summarize my personal comments and observations with respect to trends in the cone penetrometer testing. There really have been some remarkable advances, I think, in recent decades in the amount of information you could extract from modern cone penetrometer soundings. To me, it's nothing short of amazing. As I said, I've had an Excel spreadsheet for many, many years now, and it continues growing over time. It's now multiple pages of equations, and it's sometimes I even have trouble keeping track of the latest correlations that have been coming out about some of these things. But it is nothing short of amazing, I think. But we have to interpret and use this information intelligently. If you're going to get reliable data for site and project specific site characterization assessments. And just some final comments about additional cone penetrometer applications. And before closing, I just wanted to mention that this presentation has intentionally been limited to and focused on the use of the piezocone and seismic piezocone data for site characterization. The main thing I wanted to convey with this presentation is to illustrate the depth and breadth of soil properties and parameters that can be extracted from cone penetrometer data, as I think some design professionals may not be aware of how extensive the data are that we can, or the results are that we can interpret from modern cone penetrometer soundings. And I want to illustrate that in particular with respect to the Hudson Valley Varved Clays, at least for that one site in Glacial Lake Hackensack, as I think public data showing how the cone penetrometer is used in the Hudson Valley Varved Clays is very, very limited at the present time. But I would be remiss if I didn't just briefly touch on the fact that there are other reasons that we use the cone penetrometer other than to just generate soil properties and parameters. Now, historically, the way that we've used soil properties and parameters is as part of what we call the indirect method or the rational method. And with that, we take the raw data. Now, whether they're SPTN values or they're the QC, FS, U2, and V sub S from cone penetrometer soundings, and we process those data in some way, and we create a set of material properties, right, soil properties. We then use those soil properties in some generic analytical methodology. For example, you might have a theory of elasticity solution for something, and the solution requires an estimate of modulus. Now, the solution doesn't care where you get that modulus from. It just says you need a value of modulus. So you could use the value of modulus that you estimated, for example, from the cone penetrometer, use it in that analytical methodology, and you get a calculated outcome. And this is the traditional way we've been practicing foundation engineering, for example, since the beginning of modern soil mechanics in the 1920s and 1930s. And it's still a very valid approach to things. Now, for the sake of completeness, I do want to point out that one of the things that the cone penetrometer has led to is increasingly use of what we call the direct method. And in the direct method, we skip the soil properties part. We take the raw data and we process it or plug it into some application-specific analytical methodology. And what I mean is somebody has developed an empirical methodology, for example, for the axial compressive ultimate resistance of deep foundations. So you just take the QC, the FS, et cetera, from your cone penetrometer soundings. You plug it into this empirical equation or this methodology. It may be in some computer program. It may be generic. It may be proprietary. You plug it into this methodology, into this black box, if you will, and out comes a calculated outcome. This has become increasingly popular because it is very simple, and there's nothing wrong with it. I will just tell you, I certainly have used both the indirect and the direct methods extensively. If you want to see a very detailed example, just look at my presentation on tapered piles and the book that I wrote on tapered piles. I look at indirect and direct methods for tapered piles in substantial detail, both methodologies, and compare the results. And there are pluses and minuses to both approaches. My personal preference probably leans to the indirect method simply because you actually see what's going on. Okay, you can I'm not saying the indirect method is always better, but you see what is going on. And certainly when you're doing research on something and you want to see what's happening in some mathematical model you created, the indirect method is, I think, the better way to go. That having been said, the direct method can be used with great success. But the thing to be careful about with the direct method, again, is to recognize that this application-specific analytical methodology is a black box, if you will. It is empirical. It is based on some database. So you have to be very careful that you don't use it outside of the database for which it was developed. Now, in a particular case I found with the research I was doing with tapered piles is the vast majority of the direct methods that have been developed for the cone penetrometer and deep foundations, whether it's driven piles, bored piles, slash drilled shafts, whatever, is that they're not tapered. They're constant diameter, constant width. So I found that these direct methods gave you very poor correlation with measured results for tapered piles. So all I'm saying is there's nothing wrong with using direct methods. They are more popular than ever with cone penetrometer data, but you need to use them very carefully and intelligently, because never lose sight of the fact they were developed based on an empirical database. But the greater point I'm bringing up here is that the thing about the cone penetrometer is that it offers a wide variety of possibilities beyond the basic site characterization. And that really increases and adds to the cost effectiveness of using the cone penetrometer as an in situ testing tool, because you get one set of data. Now, whether you use those data to get soil properties, or you just plug them directly in an analytical methodology, or both. Perhaps you want to use multiple methods to check one against the other, which is a very reasonable thing to do in design practice. It's basically you get two for the price of one, if you will, and I think that adds to the cost effectiveness of using the cone penetration test. To illustrate this last point about the cost effectiveness of cone penetrometer testing, the very recent, very nice publication in the public domain, you can find it online, is a comprehensive design manual that was prepared under contract for the state of Minnesota DOT. And you'll find in this manual, and Dr. Main was one of the consultants who participated in the preparation of this manual, you'll find that some of the site characterization relationships in this manual are the same ones I've used in my work. Not all of them, but some of them are the same. And this manual also shows you, in addition to the site characterization part, it shows you direct method methodologies for CPT data for both shallow and deep foundation analysis. So this is a very nice example in the public domain, kind of showing all of the capabilities of the cone penetration testing for both just site characterization as well as a direct method application of the CPT data for foundation analysis. Well, with that, I want to say thank you and bring this lengthy presentation to a close. I want to first and foremost thank you for taking the time to view the presentation. I hope you found it of some use and some interest in your professional work, whether it be design related or research or both. And I of course want to thank the many people who generated material that I've referred to in this presentation, especially Dr. Paul Main and Dr. Peter Robertson. I've had the good fortune to have met both of these people on multiple occasions, and to have communicated with them many more times as well. And certainly their contribution to our knowledge about the cone penetration test cannot be rivaled. And I would be remiss if I didn't also acknowledge the geologists who have done so much to, especially Cheryl Moss at Muser Rutledge MRCE in New York City, as well as MRCE as a firm, has allowed use of data they've collected to really drastically improve our knowledge of the Pleistocene geology, especially with respect to varved clays in the New York City metropolitan area. And there are other geologists as well whose work I have used and I've acknowledged, for example, in my presentation on Kennedy Airport. So with that, again, thank you, and I will bring this presentation to a close.